Have you ever looked up at the night sky and wondered, where did it all come from? Why does the universe exist? And why are we seemingly the only existing life? Join us as we explore one of humanity's most profound questions. How did the universe begin from nothing? Imagine a time when the universe was compressed into an incredibly hot, dense singularity. This state existed approximately 14 billion years ago and is described by what we now call the Big Bang theory. According to this theory, the universe began as a singular point that suddenly expanded and continues to expand today. This expansion didn't involve an explosion in the conventional sense, but rather a swift and immense stretching of space itself. As this initial rapid expansion occurred, particles began to form, eventually coalescing into atoms and simple elements like hydrogen and helium. Over millions of years, these elements gathered under the influence of gravity, forming stars, galaxies, and ultimately, the vast cosmos we observe today. Cosmic microwave background radiation, a faint glow left over from the early universe, provides compelling evidence supporting the Big Bang theory. This radiation acts as a sort of cosmic blueprint, filling every inch of the cosmos and offering a snapshot of the universe when it was only about 380,000 years old. Observations made from satellites and telescopes have allowed scientists to measure these ancient microwaves, revealing subtle fluctuations that correspond to the initial conditions of the universe. Such scientific breakthroughs have refined our understanding, providing a glimpse into the epically grand processes that birthed the universe from a seemingly minuscule start. The evidence supporting the Big Bang theory is both compelling and diverse, offering a multifaceted confirmation of one of the most profound events in the history of our universe. One of the most significant pieces of evidence is the cosmic microwave background radiation. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, this faint afterglow is a remnant of the early universe, dating back approximately 380,000 years after the Big Bang. The CMB provides a snapshot of the infant universe, revealing temperature fluctuations that helped shape the large-scale structure of everything we see today. These minute variations, measured with extraordinary precision by instruments like the Wilkinson Microwave Anisotropy Probe and the Planck Satellite, have offered irrefutable evidence of the universe's hot, dense beginning and subsequent expansion. Another robust pillar supporting the Big Bang theory is the observable redshift of galaxies. Initially noted by Edwin Hubble in the late 1920s, this redshift reflects the fact that galaxies are moving away from us in all directions. According to Hubble's law, the farther a galaxy is, the faster it appears to be receding. This cosmic dance of galaxies uniformly moving apart is consistent with the notion that the universe is expanding, a key prediction of the Big Bang theory. Additionally, the abundance of light elements such as hydrogen, helium, and lithium observed throughout the universe aligns well with predictions made by Big Bang nucleosynthesis models. These models suggest that the conditions in the first few minutes after the Big Bang were just right for forming these elements in precise proportions. Collectively, the CMB, redshift of galaxies, and primordial element abundances weave a compelling narrative that underscores the Big Bang theory, knitting together various strands of observational data into a cohesive cosmic story. The question of what conditions existed before the Big Bang plunges us into the murky waters of the unknown, a domain where even the most advanced scientific models grapple for clarity. According to standard cosmology, the Big Bang represents the origin of time and space as we understand them. In this model, asking what came before is somewhat analogous to asking what lies north of the North Pole, essentially suggesting that the very concept of before becomes meaningless. However, speculative theories, drawing from quantum mechanics and advanced theoretical physics, offer some tantalizing ideas. One such proposal involves the notion of a pre-Big Bang state dominated by a quantum vacuum, a seething froth of probabilistic events governed by the principles of quantum mechanics. In this view, the universe could have emerged from a vacuum fluctuation, where a temporary disturbance in this quantum state resulted in a Big Bang-like event. Another intriguing hypothesis is the concept of a cyclic universe, where big bangs and big crunches occur in a continuous loop. In this model, our current expansion might eventually reverse, leading to a future collapse that precedes another Big Bang. Moreover, some theories suggest the presence of a multiverse, where our universe is just one bubble amid a frothy sea of universes, each with its own physical laws and constants. These speculative frameworks push the boundaries of our understanding, offering differing visions of what might have preceded the grand cosmic dawn marked by the Big Bang. The discovery of cosmic microwave background radiation came about through a mixture of serendipity and scientific curiosity. In the early 1960s, Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, using a large horn antenna designed for satellite communications. They aimed to measure radio waves reflected off the Milky Way, but their efforts were plagued by a persistent, mysterious noise. No matter where they pointed the antenna or how meticulously they eliminated potential sources of interference, from urban signals to environmental noise, the hum remained a constant. Upon consultation with various experts, including Robert H. Dicker at Princeton University, who had been working on similar problems, it became evident that this noise was not an artifact but rather a discovery. Dicker's team had been searching for evidence of residual thermal radiation from an early hot phase of the universe, predicted by the Big Bang theory. When Penzias and Wilson described their findings, it became clear that they had inadvertently stumbled upon the very thing Dicker's team was seeking. The noise they detected was uniformly present in all directions, a faint whisper of microwave radiation suffusing the cosmos, perfectly matching theoretical predictions. This seemingly innocuous static turned out to be the cosmic microwave background radiation, a relic from the time when the universe was about 380,000 years old and cooled enough to allow photons to travel freely. This serendipitous discovery, announced in 1965, provided an observational cornerstone for the Big Bang theory, earning Penzias and Wilson the Nobel Prize in Physics in 1978. Their work opened up new avenues of research, allowing subsequent satellites like the COBE, WMAP, and Planck missions to measure the CMB with extraordinary precision, thereby offering an unparalleled glimpse into the early universe and solidifying our understanding of its origins. While the Big Bang theory stands as a cornerstone in our understanding of the universe's origins, it is not without its limitations and unanswered questions. One major limitation revolves around the initial singularity, the point where our current laws of physics break down. The theory posits that the universe began from an infinitely dense and hot state, yet it offers little insight into the nature of this singularity, or what triggered the sudden expansion. This has led scientists to explore quantum gravity theories like string theory or loop quantum gravity, aiming to unify general relativity with quantum mechanics and provide a clearer picture of the earliest moments of the universe. Another significant limitation is the unresolved issue of dark matter and dark energy, which together account for about 95% of the universe's total mass energy content. The Big Bang theory primarily describes the visible universe, but it doesn't fully explain these mysterious components. Dark matter, invisible yet gravitationally influential, is thought to hold galaxies together, while dark energy is believed to drive the accelerated expansion of the universe. Despite myriad observations, the precise nature of both remains elusive, challenging our comprehension of cosmic evolution within the Big Bang framework. Questions like the asymmetry between matter and antimatter challenge the completeness of the Big Bang theory. According to the theory, the Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other, leaving a universe filled with energy but no matter to form stars, planets, or life. Yet the observable universe is predominantly matter, indicating some mechanism must have favored matter over antimatter, a phenomenon currently not fully explained. These gaps invite continued investigation, suggesting that while the Big Bang theory provides a robust framework, it is but one chapter in a continually unfolding cosmic narrative. Yes, there are indeed several alternative theories to the Big Bang that propose different scenarios for the origins and evolution of the universe. One notable example is the steady-state theory, which was proposed in the 1940s by Fred Hoyle, Thomas Gold, and Hermann Bondi. According to this theory, the universe has no beginning or end in time. Instead, it suggests that new matter is continually created as the universe expands, maintaining a constant density. While this theory was popular in its day, it has largely fallen out of favor due to overwhelming observational evidence supporting the Big Bang, such as the cosmic microwave background radiation and the redshift of galaxies. Another intriguing alternative is the cyclic universe theory, which posits that the universe undergoes endless cycles of big bangs and big crunches. In this model, the universe expands from a singularity, reaches a maximum size, and then contracts back into a singularity, only to bounce back and start the cycle anew. This theory seeks to address some of the questions left unanswered by the Big Bang, such as the initial conditions of the universe. Some versions of the cyclic model incorporate elements of string theory, suggesting that our universe is part of a higher dimensional brane that periodically collides with another brane, triggering repeated cycles of cosmic creation. The ekpyrotic universe is another proposal that extends the ideas of the cyclic model. Named after the ancient Greek term for conflagration, this theory suggests that the universe emerged from the collision of branes in a higher dimensional space. Unlike the traditional Big Bang, which involves an initial singularity of infinite density and temperature, the ekpyrotic model posits that the universe began from a cold, nearly empty state and gained energy from these brane collisions. Though these alternative theories are fascinating and offer fresh perspectives, they face their own sets of challenges and require further empirical evidence to gain broader acceptance within the scientific community. They nevertheless serve as important reminders of the complexity and mystery that still surround our understanding of the cosmos. Measuring the age of the universe is an accomplished feat that combines several sophisticated methods, each reinforcing the other to refine our understanding. One primary approach involves studying the cosmic microwave background radiation. This faint afterglow from the early universe, first detected by Arno Penzias and Robert Wilson in 1965, holds crucial information about the early conditions of the cosmos. Detailed measurements by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have provided data on the slight temperature fluctuations in this background radiation. By analyzing these fluctuations and the universe's overall expansion rate, scientists can estimate the universe's age. Current estimates derived from the CMB suggest the universe is approximately 13.8 billion years old. Another method utilizes the Hubble constant, which describes the rate at which the universe is expanding. First observed by Edwin Hubble in the 1920s, this metric involves measuring the redshift of distant galaxies. The further they are, the faster they seem to be receding from us. By determining the Hubble constant with high precision and extrapolating backward, astronomers can estimate the time it would take for galaxies to reach their current separations from an initial singularity, thereby providing an age for the universe. Contemporary techniques improve upon Hubble's initial measurements using advanced telescopes and observational data, such as those from the Hubble Space Telescope and other ground-based observatories. Additionally, astronomers analyze the oldest star clusters or globular clusters within our galaxy. These clusters contain ancient stars whose properties and life cycles are well understood. By measuring the luminosity and temperature of these stars and using models of stellar evolution, scientists can estimate their ages. These ages serve as a lower limit because the universe itself must be at least as old as the oldest stars it contains. Combining these independent lines of evidence, CMB measurements, the Hubble constant, and stellar ages, has allowed scientists to converge on a consistent and robust age for the universe, reinforcing the credibility of their methods and deepening our understanding of cosmic history. Singularities play a pivotal role in the conceptual foundation of the universe's origin, as they mark points where our current understanding of physics reaches its limits. A singularity, in the context of cosmology, refers to a region characterized by extremely high density and gravitational force, where space-time curvature becomes infinite. In the Big Bang model, the universe began from such a singularity, an infinitely dense point that contained all the mass and energy of the universe compressed into an almost unimaginably small volume. The notion of a singularity arises from the equations of general relativity formulated by Albert Einstein. General relativity describes how gravity governs the motion of objects and the structure of space-time. When these equations are applied to the universe on a cosmic scale, They suggest that if we trace the expansion of the universe backward in time, we reach a state where the density and temperature become infinitely high. This theoretical moment is termed the initial singularity. However, it's vital to note that while general relativity predicts such a singular state, it cannot fully describe conditions at or before the singularity due to the breakdown of the laws of physics as we know them. Singularities also appear in the study of black holes, another context that highlights their enigmatic nature. Inside a black hole, matter is thought to collapse into a singularity, a point where gravitational forces are so extreme that not even light can escape. This raises intriguing parallels and questions about the nature of singularities in both the microcosm of black holes and the macrocosm of the entire universe. To truly understand the role of singularities in the origin of the universe, scientists are exploring theories that merge general relativity with quantum mechanics. Quantum gravity theories like string theory and loop quantum gravity aim to provide a more comprehensive understanding by incorporating quantum effects, potentially resolving the paradoxes presented by singularities. Thus, singularities symbolize both a starting point in cosmic history and a frontier pushing the boundaries of modern physics. Redshift offers a compelling window into the expanding nature of our universe, acting as a cosmic Doppler effect that astronomers have expertly utilized to unravel the dynamics of galaxies and cosmic structures. In simplest terms, redshift refers to the stretching of light to longer, redder wavelengths as objects in the universe move away from us. When a galaxy recedes, the light it emits gets stretched, causing its spectral lines to shift toward the red end of the spectrum. Edwin Hubble's groundbreaking observations in the 1920s first revealed this phenomenon, showing that distant galaxies exhibit a redshift that increases with their distance from Earth, indicating that the universe is expanding. Hubble's discovery was monumental because it provided the first concrete evidence that the cosmos was not static but dynamically evolving. By measuring the redshift of various galaxies, Hubble derived a relationship now known as Hubble's law, the observation that the recessional velocity of a galaxy is directly proportional to its distance from us. This linear relationship allowed astronomers to estimate the rate of cosmic expansion known as the Hubble constant. By determining this constant with increasing precision, modern telescopes such as the Hubble Space Telescope and more recent instruments like the James Webb Space Telescope refine our understanding of the universe's rate of expansion. Redshift is not just a tool for measuring the speed at which galaxies move away, it also allows scientists to peer into the universe's past. Because light from distant galaxies takes millions or even billions of years to reach us, we observe these celestial objects as they were in the distant past. Consequently, redshift helps construct a timeline of cosmic history, revealing how galaxies, clusters, and large-scale structures have evolved over billions of years. Furthermore, as we observe higher redshift galaxies, we encounter conditions closer to the Big Bang, allowing us to study phenomena like the formation of the first stars and galaxies, the distribution of dark matter, and the role of dark energy in accelerating cosmic expansion. Redshift data also synergize with other cosmological observations, such as the cosmic microwave background radiation and the distribution of galaxy clusters, to fine-tune models of the universe's geometry, age, and composition. Together, these observations form a coherent and increasingly detailed picture of a universe that has been expanding for approximately 13.8 billion years, an insight powered largely by the telltale shifts in the spectrum of starlight. The question of what triggered the Big Bang is one of the most profound mysteries in cosmology, and while definitive answers remain elusive, several leading hypotheses aim to provide potential explanations. One prominent hypothesis involves quantum fluctuations in a pre-existing state. According to this hypothesis, before the Big Bang there might have been a quantum vacuum, an almost empty space with unpredictable energy fluctuations due to the laws of quantum mechanics. These fluctuations could have caused a rapid and immense release of energy, sparking the expansion that led to the birth of our universe, as described by the Big Bang. Another intriguing hypothesis is the concept of cosmic inflation, introduced by physicist Alan Guth in the early 1980s. Inflation theory proposes that a fraction of a second after the Big Bang, the universe underwent an exponential expansion driven by a field known as the inflaton. This rapid expansion smoothed out any initial irregularities, and set the stage for the slower expansion we observe today. While inflation explains the conditions immediately following the Big Bang, it also raises the question of what caused inflation itself. Some models suggest that inflation was triggered by energy conditions in a higher dimensional space or multiverse. Some models suggest that inflation was triggered by energy conditions in a higher dimensional space or multiverse, where regions of space with different energy densities go through periodic phases of rapid expansion. This leads to the idea that our universe could be just one of many pocket universes within a vast multiverse. A related concept is the ekpyrotic universe, which suggests that the Big Bang was initiated by the collision of higher dimensional branes within a larger cosmological framework. In this scenario, our four-dimensional universe is part of a multi-dimensional space where branes exist and occasionally collide. These collisions produce immense amounts of energy, resulting in a Big Bang event. The ekpyrotic model not only attempts to explain the conditions leading up to the Big Bang, but also offers mechanisms for cyclic universes, where each Big Bang is part of an eternal cycle of creation and destruction. Some theories consider the role of quantum cosmology in describing the universe's origins. These models attempt to unify general relativity with quantum mechanics, suggesting that the universe may have emerged from a quantum state without a classical singularity. Proposals include the Hartle-Hawking no-boundary condition, which posits that the universe is finite but unbounded, akin to the surface of a sphere, eliminating the need for an initial singularity. This condition implies that time itself might have had a different character near the Big Bang, blending spatial and temporal dimensions in ways that defy our everyday understanding. While these hypotheses offer fascinating glimpses into the possible triggers of the Big Bang, they remain speculative until further observational evidence and theoretical developments can provide more concrete answers. Each hypothesis pushes the boundaries of our understanding and underscores the depth and complexity of questions concerning the origins of our universe. The theory of eternal inflation is a fascinating extension of the concept of cosmic inflation, which itself was proposed to address several key problems in the standard Big Bang model, such as the horizon and flatness problems. While cosmic inflation posits a brief period of extremely rapid expansion in the early universe, lasting a tiny fraction of a second, eternal inflation suggests that this process might never completely end. Instead, it proposes that inflation is an ongoing phenomenon, leading to the creation of an infinite number of bubble universes within a larger multiverse. In the standard inflationary scenario, a hypothetical field called the inflaton drives rapid expansion due to its high energy state. As the universe expands, the inflaton field rolls down its potential energy landscape towards a minimum energy state, ultimately transitioning to the slower expansion observed today. However, in the eternal inflation model, quantum fluctuations cause different regions of the universe to experience varying rates of inflation. While some regions complete their transition to a slower expansion, others continue inflating due to these fluctuations. This generates a fractal-like structure where pocket universes or bubble universes form in regions where inflation has ended, while the surrounding space continues to inflate indefinitely. The notion of eternal inflation suggests that what we perceive as our universe is just one of countless bubbles that have nucleated out of this eternally inflating space. Each of these bubble universes can have different physical properties, laws of physics, and constants, potentially varying in fundamental ways from our own. This multiverse framework provides a potential solution to some fine-tuning problems in physics, like the exact values of cosmological constants required for life to exist. If there are an infinite number of universes with varying properties, it becomes statistically plausible that at least some of them would have the right conditions for life as we know it. Eternal inflation also has profound implications for our understanding of the cosmic landscape. Because the regions where inflation continues are constantly expanding faster than the speed of light can travel within them, these bubble universes are essentially isolated from one another. This makes direct interaction or observation between different bubbles practically impossible, leading to challenges in validating the theory through empirical evidence. Nevertheless, eternal inflation offers a compelling narrative that expands our cosmological horizons suggesting that our observable universe is but a tiny speck in a vast and continually expanding multiverse. Chaotic inflation, introduced by physicist Andre Linde in the early 1980s, offers a distinct perspective within the broader framework of inflationary theories. Unlike the original inflationary model proposed by Alan Guth, which assumes a specific initial condition where the universe existed in a high-energy false vacuum state, chaotic inflation posits a more random and less structured beginning. This theory suggests that inflation can start in any region where the inflaton field, a hypothetical field responsible for driving inflation, has sufficiently high energy. Consequently, chaotic inflation does not require a special initial state and can begin in regions with varying energy configurations, making it more versatile and generalizable. One of the key differences between chaotic inflation and other models is its reliance on the dynamics of the inflaton field's potential energy. In chaotic inflation, the potential energy landscape of the inflaton field is typically much simpler, often taking forms like a quadratic or quartic potential. Here, the inflaton field's value can be large and chaotic in different regions of the early universe. As the inflaton values randomly distributed across space, certain regions will naturally have sufficiently high energy to undergo rapid exponential expansion. This randomness makes the initiation of inflation almost inevitable in some regions, contrasting with earlier models that required more finely tuned conditions. Chaotic inflation also naturally leads to the concept of eternal inflation, which posits that inflationary regions can continually spawn new inflating regions, creating a self-sustaining fractal structure of an inflating universe. As different regions of spacetime undergo inflation, they become causally disconnected from one another, leading to an enormous, possibly infinite multiverse composed of countless bubble universes. Each of these bubble universes could have different properties and physical constants, providing a natural explanation for the observed fine-tuning of our universe without the need for precise initial conditions. Another aspect that sets chaotic inflation apart is its adaptability to various high-energy physics theories, including string theory and quantum cosmology, making it a versatile framework for exploring the early universe's properties. The simplicity and generality of chaotic inflation have made it an attractive model for cosmologists, leading to robust predictions that can be tested through observations of the cosmic microwave background radiation, large-scale structure, and other cosmological phenomena. Overall, chaotic inflation offers a compelling, flexible, and less fine-tuned approach to understanding the early universe's rapid expansion, distinguishing itself from other inflationary theories by its reliance on the inherent randomness and simplicity of the inflaton field's potential energy. This framework not only aligns well with empirical observations, but also opens up intriguing possibilities for the existence of a vast and diverse multiverse. The concept of a multiverse, which has captivated both scientists and the public alike, proposes that our universe is just one of potentially many universes that exist simultaneously. Each of these universes, collectively termed the multiverse, could have different physical laws, constants, and initial conditions, potentially giving rise to environments vastly different from our own. This idea lifts the veil on the traditional understanding of a solitary cosmos, inviting speculation about an endless diversity of realities. Several theories support the notion of a multiverse, each offering its own perspective. One prominent framework comes from cosmological inflation, particularly the theory of eternal inflation. In this model, rapid expansion of space, driven by the inflaton field, continues indefinitely in some regions, while other regions stop inflating and form isolated bubble universes. These bubbles are causally disconnected from each other, meaning that what happens in one bubble universe does not affect the others. Consequently, the multiverse from this viewpoint is a vast, frothy landscape of countless isolated universes, each potentially following different physical laws. String theory provides another fertile ground for the multiverse concept through its notion of a higher dimensional brane world. According to string theory, our universe could be a three-dimensional slice or brane floating within a higher dimensional space. Collisions or interactions between different branes can give birth to new universes, each residing on its own brane with unique physical properties. This brane world scenario complements the idea of a multiverse by extending it into higher dimensions, where countless branes, and thus countless universes, exist. Quantum mechanics also contributes to multiverse hypotheses through the many worlds interpretation, originally formulated by Hugh Everett in the 1950s. In this interpretation, every quantum event that involves a choice or randomness results in a branching of the universe into multiple, equally real versions. For example, if a particle can take two different paths, the universe splits into two. In one universe, the particle takes one path. In the other, it takes the alternative path. This continual branching results in a vast, ever-growing ensemble of parallel universes, each representing different outcomes of quantum events. Moreover, some philosophical and theoretical arguments appeal to the anthropic principle, which suggests that the conditions we observe in our universe are fine-tuned for the emergence of life, because only in such a universe could observers exist to notice these conditions. In the context of a multiverse with many different physical settings, it's statistically probable that some universes, like ours, will have the right conditions for life. The multiverse is a theoretical construct that posits the existence of multiple universes beyond our observable cosmos. Supported by various frameworks in modern physics, ranging from cosmic inflation and string theory to quantum mechanics and the anthropic principle, the multiverse concept offers profound implications. It challenges our understanding of reality, suggesting that what we perceive as the entirety of existence may be just one small part of a grander, more complex cosmic tapestry. Eternal inflation leads to the concept of a fractal universe by suggesting that inflationary processes can perpetuate themselves indefinitely, creating a complex, self-replicating structure on cosmic scales. This idea stems from quantum fluctuations that occur during the inflationary phase of the early universe. In the context of inflation, the inflaton field, responsible for this rapid expansion, does not have a uniform energy state. Instead, quantum mechanics ensures that the field experiences random fluctuations. These fluctuations can cause regions of spacetime to inflate at different rates. While some regions transition out of the inflationary phase and form bubble or pocket universes, like our own, other regions continue to inflate at an exponential rate. This process creates a scenario where pockets of non-inflating space, our observable universes, are embedded within an ever-expanding inflating space. Because the inflating regions don't all stop inflating at once, new bubble universes continue to form in perpetuity. Each of these bubbles can be thought of as an individual branch on a colossal, ever-growing tree. The self-similar nature of this structure, where each bubble can spawn further bubbles, with inflating regions giving rise to more inflating regions, resembles a fractal pattern. In a fractal, a complex pattern is recursively generated on ever smaller scales, leading to an intricate and infinitely detailed structure. Similarly, inflating regions within the universe perpetually generate new structures on various scales, exhibiting a recursive, fractal-like complexity. This fractal nature of the universe extends to its geometry and topology. As inflation continues in certain regions, space itself expands at an exponential rate, stretching the geometric landscape and creating a frothy, irregular network of inflating and non-inflating regions. Each bubble universe can have different physical laws and constants, adding layers of complexity and diversity to this fractal cosmic structure. Eternal inflation thus portrays the universe not as a singular uniform entity, but as a dynamically evolving hierarchical system. This system is characterized by continuous exponential growth punctuated by the birth of countless bubble universes. These bubbles, or separate domains, form a vast self-similar pattern that defies our conventional understanding of spatial and temporal scales. By embracing the fractal nature of eternal inflation, cosmologists can address some of the most profound questions about the origins, structure, and diversity of the cosmos, offering a tantalizing glimpse into the endless possibilities of the multiverse. Eternal inflation is a fascinating concept, suggesting that our universe is just one bubble among an infinite sea of other bubble universes. The evidence supporting this theory ties back to the discovery of quantum fluctuations in the cosmic microwave background radiation, remnants from the early stages of the Big Bang. These minute fluctuations, first detected by the COBE satellite in the early 1990s and later confirmed by the WMAP and Planck satellites, demonstrate that the universe underwent a rapid expansion phase known as inflation. In this scenario, different regions of space could undergo inflation at different rates, leading to pockets forming their own expanding universes while inflation continues elsewhere. This supports the idea that inflation never completely stops, thus setting the stage for an eternally inflating cosmos filled with multiple, potentially infinitely many bubble universes. Additionally, the theoretical underpinnings of eternal inflation align well with our understanding of quantum mechanics and general relativity, two pillars of modern physics. In quantum field theory, vacuum states can fluctuate, temporarily allowing energy to wane or wax unpredictably, instigating pockets of inflation. These bubbles eventually pinch off to become separate universes. Nobel laureate theoretical physicists such as Alan Guth and Andre Linde have postulated scenarios where inflation, driven by a scalar field known as the inflaton, continues eternally because the inflaton's potential never entirely stabilizes. These scientific insights, when combined with observational data, create a compelling case for the perplexing, wondrous model of eternal inflation, painting a picture of a cosmos far grander and more intricate than a single Big Bang universe. Eternal inflation provides an elegant solution to the horizon problem, which puzzles cosmologists because of the uniform temperature of the cosmic microwave background radiation across vast regions of space that seemingly haven't had enough time to exchange information or energy since the Big Bang. To understand how eternal inflation addresses this, we need to delve into the nature of inflation itself. During inflation, our universe expanded extraordinarily rapidly, much faster than the speed of light. This dramatic expansion meant that regions of space that were once close together were flung far apart very quickly. Because inflation smooths out any initial irregularities in the energy density of the universe, it ensures that the regions within our observable universe, which appear to be in equilibrium with each other, actually originated from a much smaller, causally connected area before inflation stretched them out. Effectively, the universe's rapid inflationary phase allowed these regions to harmonize their temperatures when they were still close to each other, before being blown up to astronomical distances. Thus, when we observe the cosmic microwave background radiation and see its uniformity, it's because these regions were once close enough to exchange information and energy thanks to inflation, thereby solving the horizon problem. In the context of eternal inflation, each bubble or pocket universe, including ours, inherits this smoothing characteristic. Each new universe sprouts from the inflating spacetime and undergoes its own brisk inflationary period, setting up favorable initial conditions like temperature uniformity. This renders the horizon problem not merely a feature of our universe, but an intrinsic resolution embedded within the larger framework of eternal inflation, where the laws of physics work universally to create homogeneous conditions in each nascent bubble universe. Quantum fluctuations play a pivotal role in the mechanism of eternal inflation, acting as the seeds that drive the continuous creation of new bubble universes within the ever-expanding cosmic landscape. To grasp their importance, imagine the inflaton field, a hypothetical scalar field responsible for driving the universe's inflationary phase. As the universe swells, the inflaton field experiences tiny random fluctuations due to quantum mechanics. These fluctuations cause certain regions to momentarily have slightly higher or lower energy densities than their surroundings. In regions where the inflaton field's energy remains higher due to a quantum fluctuation, inflation continues unabated. This means that while some pockets of the universe might stop inflating and settle down into a more stable state, forming what we perceive as separate bubble universes, other regions will keep inflating. The process is much like an expanding foam, where different bubbles form and grow at various stages but collectively contribute to the overall growth. This perpetuation of inflation in certain regions due to quantum fluctuations underlies the concept of eternal inflation, ensuring that the cosmos is continuously birthing new universes. Moreover, these quantum fluctuations give rise to the initial density variations that later evolve into the large-scale structures we observe in our universe today, such as galaxies and clusters of galaxies. As each bubble universe emerges with its unique set of fluctuations, it can develop distinct characteristics and physical laws. Thus, quantum fluctuations not only instigate and sustain the eternal inflationary process, but also imbue each bubble universe with the potential for varied and rich cosmic evolution. This intricate interplay between quantum mechanics and cosmology underscores the staggering complexity and perpetual creativity embedded within the tapestry of existence. In the framework of eternal inflation, Bubble universes form through a fascinating interplay between inflationary energy and quantum fluctuations. Picture the inflaton field as a vast rolling landscape where the energy levels can vary due to tiny quantum jitters. As some regions of this inflating space undergo these random fluctuations, they hit lower energy sets where inflation slows dramatically or even stops. These pockets of decreased inflation effectively pinch off, stabilizing and expanding more slowly, becoming distinct bubble universes with their own set of physical properties and laws. The reason these bubbles form lies in the nature of the inflaton field and how it interacts with space-time. When a region of space experiences a drop in the inflaton field's energy due to a quantum fluctuation, this region exits the inflationary phase and begins to cool and coalesce into a new, separate universe. While this bubble universe matures, the surrounding high-energy space continues to inflate. This creates a dynamic, frothy multiverse where new bubbles constantly emerge within the inflating sea. This conceptual model is akin to an ever-expanding loaf of raisin bread, where each raisin represents a bubble universe. As the bread dough, the inflating space, rises and expands, new raisins, bubble universes, form throughout the loaf. Each of these bubble universes can have their own characteristics and physical constants because they develop somewhat independently, shaped by the unique conditions present at their birth. The birth of bubble universes in eternal inflation is a continual, never-ending process fueled by the interplay of cosmic expansion and quantum mechanics. It paints a picture of a multiverse that's both dynamic and perpetually burgeoning with new realms of possibility, each potentially vastly different from our own. The possibility of observing or interacting with other universes within the framework of eternal inflation remains one of the most tantalizing questions in cosmology. According to our current understanding, interacting with or directly observing other bubble universes is highly improbable, if not outright impossible, due to several fundamental reasons rooted in the nature of inflation and the structure of space-time. When a bubble universe forms, it does so in a vast, exponentially expanding space. The distances between these bubble universes grow at a pace that outstrips the speed at which signals or particles could travel, effectively isolating each universe within its own cosmic horizon. Moreover, the boundaries between these bubble universes are fraught with exotic and extreme conditions. These boundaries, known as domain walls, could possess varying energy densities, causing immense gravitational effects or even hazardous environments that would make any form of traversing or communication impractical with our current understanding of physics. The nature of each bubble's space-time fabric might be so profoundly different that they are fundamentally incompatible with one another, posing additional barriers to any conceivable form of interaction. However, while direct observation or interaction may be off the table, indirect evidence could still be within reach. For instance, if two bubble universes happen to collide during their formative phases, the aftermath of such a collision could leave detectable imprints in the cosmic microwave background radiation in the form of specific anomalous patterns. Scientists are actively seeking such signatures, analyzing the high-precision data from missions like the Planck satellite. Additionally, theoretical innovations in quantum gravity and string theory might one day provide frameworks that allow for the conceptualization of how these interactions could occur, even if only in terms of information exchange on a highly abstract level. Thus, while the direct observation or interaction with other universes seems elusive given our current technology and understanding, the quest to uncover indirect evidence continues to drive scientific inquiry. It keeps open the tantalizing possibility that one day we may glean insights into the nature of a multiverse teeming with realms as rich and complex as our own. Eternal inflation fundamentally alters our perception of the universe's size, suggesting it is not just vast, but potentially infinite. In the standard Big Bang model, the universe is already enormously large, expanding from an initial singularity around 13.8 billion years ago. However, the concept of eternal inflation introduces a scenario where our observable universe is just a tiny fraction of a much larger, eternally inflating multiverse. During the inflationary phase, space expands exponentially, meaning that even tiny regions of the inflating space become immensely large in an incredibly short period. Since this process is continuous and unending in some regions due to the stochastic nature of the inflaton field, it results in a never-ending creation of new bubble universes. Each bubble universe, like the one we inhabit, might be finite in size, but the space in which they form is relentlessly expanding and generating new bubbles. Hence, the multiverse comprising all these bubble universes is not just vast but potentially has no bounds, meaning it could be infinite. This has profound implications for our understanding of the cosmos. First, it challenges the notion that our observable universe is all there is. It becomes just one of countless other universes. Second, it implies that the true scale of reality is so large that many physical phenomena or constants we take as fundamental might vary in other bubbles. For instance, the laws of physics or the fundamental constants like the speed of light or gravitational strength could differ from one bubble universe to another. Moreover, the sheer size suggested by eternal inflation adds a layer of complexity to the cosmological principle, which assumes that on large scales, the universe is homogeneous and isotropic. While this may hold true within individual bubble universes, the multiverse as a whole might exhibit incredible diversity. The implications for other fields, including philosophy and metaphysics, are equally staggering, prompting re-evaluations of concepts like existence and reality. By expanding our idea of the universe's size to potentially infinite proportions, eternal inflation opens up realms of contemplation and discovery that are as boundless as the cosmos it seeks to describe. The anthropic principle is a philosophical consideration that aims to explain why the universe's physical constants and laws appear finely tuned to support the existence of intelligent life, particularly human life. At its core, the anthropic principle suggests that the universe's properties must be compatible with the conscious beings observing it. Otherwise, those beings wouldn't be here to make the observation in the first place. There are two main formulations of this principle: the weak anthropic principle, WAP, and the strong anthropic principle. The weak anthropic principle posits that we can observe the universe's properties because they allow for our existence. For example, the constants governing the strength of electromagnetic forces or the cosmological constant are precisely what they need to be for stars to form, for chemistry to happen, and for life to evolve. In a multiverse scenario brought forward by eternal inflation, this principle implies that numerous universes with varying physical laws and constants exist, but we find ourselves in one of the rare universes where conditions are just right for life. Conversely, the strong anthropic principle goes a step further by proposing that the universe must have those properties that allow life to emerge and evolve. Some interpretations of SAP even suggest that the universe is compelled to evolve in a way that fosters life and consciousness, a viewpoint that blends cosmology with deeper metaphysical implications. The anthropic principle's implications are profound. It offers a potential explanation for why our universe seems so precisely tailored for life without invoking a creator or designer. It aligns well with the many worlds interpretation of quantum mechanics and the eternal inflation model in cosmology, where different universes within the multiverse have different properties, and only a fraction of these universes can harbor life. Critics argue that the anthropic principle is tautological or non-falsifiable. However, its contribution to our understanding of cosmic fine-tuning remains a crucial and thought-provoking element of contemporary scientific discourse. Physical constants play a crucial role in shaping the universe's conditions, and consequently, the possibility of life as we know it. These constants determine the fundamental forces and interactions that govern everything from the smallest subatomic particles to the largest cosmic structures. Even slight variations in these constants could result in a vastly different universe, potentially hostile to life. Take, for example, the gravitational constant. It's an extraordinarily small number, but it dictates the strength of gravity, which in turn influences the formation of stars and galaxies. If gravity was significantly stronger, stars would burn out much faster, providing a much shorter window for life to develop. Conversely, if gravity were weaker, stars might never ignite and galaxies might not form, leading to a cold, dark universe devoid of complexity. Another critical constant is the electromagnetic force, determined by the fine structure constant. This constant affects how atoms interact and bond to form molecules. A considerable deviation in this constant could mean that the stable atoms and molecules necessary for chemistry, and therefore biochemistry, wouldn't form. For instance, if the fine structure constant were slightly stronger or weaker, it could alter the energy levels within atoms, compromising the stability of essential elements like carbon, and thus eliminating the possibility of carbon-based life forms. The strong nuclear force, responsible for holding protons and neutrons together in atomic nuclei, is equally vital. If this force were only a few percent stronger, nuclear fusion in stars would be so efficient that nearly all hydrogen would be converted to helium, leaving no room for the formation of other essential heavier elements. A weaker nuclear force, on the other hand, might prevent nuclei from forming altogether, undermining the universe's elemental diversity needed for complex chemistry and life. These fine-tuned constants are often cited in discussions of the anthropic principle, which posits that we observe these precise values because only universes with such values can support observers like us. The delicate balance imbued within these constants is a cornerstone of why our universe can host life, providing a stable and hospitable environment where complexity can emerge, evolve, and thrive. Such considerations continually fascinate scientists and philosophers alike, prompting deeper questions about the nature of our universe and the potential existence of other realms with different physical laws. The fine-tuning of the universe for life is an intriguing aspect that has captivated scientists and philosophers alike. It refers to the observation that various physical constants and conditions in the universe are precisely calibrated to allow for the existence of life, particularly intelligent life. Here are some compelling examples of fine-tuning. The cosmological constant, often associated with dark energy, dictates the rate at which the universe is expanding. If this constant were even slightly different, the universe would either have expanded too rapidly for galaxies to form or collapsed back on itself too quickly. The precise value we observe allows for a stable, gradually expanding universe where stars and planets can form over billions of years, providing a timeframe conducive to the evolution of life. The strong nuclear force is a fundamental force that holds protons and neutrons together within atomic nuclei. It is finely balanced. If it were just 2% stronger, nuclear fusion in stars would proceed so efficiently that almost all hydrogen would be converted to helium and other heavier elements, leaving little hydrogen to form water. If it were 2% weaker, atomic nuclei wouldn't hold together, and the universe would lack the stable elements necessary for forming complex structures, including life. The weak nuclear force is responsible for processes like beta decay, vital for nuclear reactions inside stars. If the weak force were significantly stronger or weaker, the delicate balance of the fusion processes in stars would be disrupted. This could hinder the production of heavy elements like carbon and oxygen, which are essential for life. Furthermore, changes in the weak force's strength could impact the rate of supernova explosions, which scatter heavy elements throughout the universe, enriching star-forming regions with the materials necessary for planets and life. The electromagnetic force, governed by the fine structure constant, this force controls how atoms hold together and interact. A slight change in the electromagnetic force's strength would alter the energy levels within atoms, making chemistry as we know it impossible. For instance, essential elements like carbon might not form stable compounds, severely limiting the chemistry needed for life. The mass ratio between electrons and protons is approximately 1 to 1836. This ratio affects the chemistry of atoms and molecules. If this ratio were significantly different, the bonding properties of atoms would be altered, potentially preventing the formation of molecules necessary for life, such as water and organic compounds. These examples of fine-tuning highlight the delicate balance required for a life-sustaining universe. The precise values of these constants and conditions appear almost designed to allow for the complex chemistry and long-term stability that life depends on. While some see this as evidence of design or purpose, others consider it a natural consequence of the anthropic principle, where only universes with such fine-tuned parameters could harbor observers capable of pondering their existence. Regardless of the interpretation, the fine-tuning of the universe remains a profound and compelling feature of our cosmos. The type of star around which a planet orbits significantly influences the planet's habitability, affecting everything from its temperature and atmosphere to the potential for life-sustaining conditions. Different stars emit varying amounts and types of radiation, have diverse lifespans, and can influence planetary environments through stellar activity, such as flares and winds. These factors collectively shape the habitable zone, a region where conditions might allow liquid water to exist, a critical ingredient for life as we know it. Sun-like stars, or G-type main sequence stars, are considered ideal candidates for habitable planets. The Sun, a G2V star, has a stable luminosity and a relatively long lifespan of around 10 billion years, providing a long window during which life can potentially develop and evolve. The habitable zone around a Sun-like star is also at a convenient distance where water can remain liquid. Planets in this zone can enjoy stable climates that are not too hot or cold, fostering the development of complex life. On the other hand, smaller M-type stars known as red dwarfs are the most common stars in the galaxy and have lifespans that can extend into trillions of years. While this longevity provides ample time for life to potentially evolve, red dwarfs present unique challenges. Their habitable zones are much closer to the star due to their lower luminosity. This proximity increases the likelihood of tidal locking, where one side of the planet perpetually faces the star, possibly creating extreme temperature gradients. Additionally, red dwarfs are prone to intense and frequent stellar flares, which can strip away planetary atmospheres or bathe the surface in harmful radiation, posing a significant threat to the development of life. Conversely, larger and hotter stars such as A-type or O-type stars have much shorter lifespans ranging from a few million to a few 100 million years. While their higher energy output widens the habitable zone, their rapid aging and eventual violent demise through supernova explosions don't provide enough time for complex life forms to develop. The intense radiation from these stars can also be destructive to any nascent biospheres. K-type stars, or orange dwarfs, present an intriguing middle ground. They are cooler and dimmer than G-type stars, but more stable than red dwarfs, with long lifespans ranging from 15 to 30 billion years. Their habitable zones are also closer than those of Sun-like stars, but not so close as to cause tidal locking. Planets around K-type stars might therefore have a better chance at maintaining stable climates and longer periods for biological evolution. Thus, the habitability of a planet is greatly influenced by the characteristics of its parent star. While Sun-like stars provide a stable, conducive environment for life's emergence and evolution, other types of stars present unique opportunities and challenges. Whether in the habitable zones of long-lived red dwarfs, the more energetic environments of orange dwarfs, or the short-lived realms of massive stars, each stellar type contributes to the rich tapestry of potential habitats in our galaxy. Water is often considered the cornerstone of planetary habitability, primarily because it serves as a crucial medium for biochemical reactions and plays a vital role in regulating planetary climates and environmental conditions. Its unique properties make it indispensable for life as we know it, providing both a solvent for life's chemical processes and a medium that helps stabilize environments conducive to sustaining life. One of the key roles of water is as a universal solvent. Many of the complex biochemical reactions necessary for life, such as those involving proteins, nucleic acids, and cellular structures, dissolve and interact within water. This aqueous environment allows for the efficient transfer and transformation of energy and nutrients, facilitating vital processes like metabolism, DNA replication, and cellular respiration. The polarity of water molecules enables it to dissolve a wide range of substances, making it an ideal medium for transporting essential nutrients and waste products within living organisms. Water also influences climate and temperature regulation on a planetary scale. It has a high specific heat capacity, meaning it can absorb and store large amounts of heat without experiencing significant changes in temperature. This property helps moderate a planet's climate, preventing extreme temperature fluctuations that could be detrimental to life. Earth's vast oceans, for example, act as thermal buffers, absorbing heat during the day and releasing it at night, thus maintaining relatively stable and hospitable conditions over long periods. Furthermore, the existence of liquid water on a planet's surface can indicate a stable and relatively benign atmosphere. A stable atmosphere is essential for protecting life from harmful solar radiation and maintaining a pressure that allows liquid water to remain stable. Planets within their star's habitable zone, where temperatures are just right for liquid water to exist, are prime candidates for habitability. This zone, often referred to as the Goldilocks zone, provides a range where conditions are neither too hot nor too cold, but just right for water to remain in liquid form. Water also contributes to the dynamic processes that sustain a planet's geological and atmospheric equilibrium. On Earth, for instance, the water cycle, including processes like evaporation, condensation, and precipitation, plays a crucial role in weather patterns and the distribution of heat across the planet. Additionally, water is a key agent in the formation of soils and rocks through erosion and sedimentation, creating diverse habitats and recycling nutrients essential for life. Moreover, water interacts with other critical molecules like carbon dioxide through processes such as the carbonate-silicate cycle, which helps regulate atmospheric CO2 levels. This interaction aids in maintaining a stable greenhouse effect, crucial for keeping a planet warm enough to support life. Water's role in making a planet habitable extends beyond just being a solvent for biochemical reactions. It is integral to climate moderation, temperature regulation, and geological and atmospheric processes that create and maintain environments where life can thrive. Its unique properties make it an essential component in the search for potentially habitable exoplanets, as the presence of liquid water significantly increases the likelihood of finding life beyond Earth. The distance of a planet from its parent star is one of the most critical factors influencing its habitability, mainly because it determines the planet's surface temperature and the potential for liquid water, a key ingredient for life as we know it. This optimal range of distances is commonly referred to as the habitable zone or the Goldilocks zone, an area around a star where conditions are just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. Close to the star, within what is known as the inner edge of the habitable zone, a planet may face intense heat, leading to conditions similar to those on Venus. Here, the star's radiation could cause any surface water to evaporate rapidly, resulting in a runaway greenhouse effect, where water vapor, a potent greenhouse gas, traps more heat. This could lead to extremely high surface temperatures, making the planet uninhabitable. The intense heat can also strip away the planet's atmosphere over time, further diminishing its potential to support life. Conversely, planets located beyond the outer edge of the habitable zone may be too far from their star, resulting in frigid conditions where any water present would be frozen into ice. Such environments, akin to the conditions on Mars or the moons of the outer solar system like Europa or Titan, might harbor some subsurface liquid water beneath ice layers, but the surface conditions would be too cold to support liquid water and thus life as we traditionally understand it. The habitable zone's position isn't static. It varies depending on the star's type and luminosity. For instance, Sun-like stars, G-type main sequence stars, have a habitable zone that ranges approximately from 0.95 to 1.4 astronomical units, AU, from the star, with 1 AU being the average distance between Earth and the Sun. For smaller, cooler M-type stars or red dwarfs, the habitable zone is much closer, sometimes just a fraction of an AU, due to their lower energy output. This proximity poses challenges such as increased stellar flares and the potential for tidal locking, where one side of the planet permanently faces the star, leading to extreme temperature differences between the day and night sides. In addition to the star type, other factors also modify the impact of distance on habitability. For example, a planet with a thick atmosphere rich in greenhouse gases like carbon dioxide can trap more heat, extending the habitable zone farther from the star. An excellent case is Earth, whose atmosphere and oceans help regulate temperature and distribute heat more evenly across the globe. Likewise, a planet with a reflective ice or cloud cover can deflect a significant amount of the star's energy, potentially allowing it to remain habitable even closer to the star. Furthermore, orbital eccentricity, or how elliptical a planet's orbit is, can also affect habitability by causing significant variations in distance from the star over a single orbit, leading to wide temperature swings. Planets in almost perfectly circular orbits have more stable climates, which are generally more conducive to life. The distance of a planet from its star profoundly affects its surface temperature and the potential for liquid water, thus heavily influencing its habitability. While the habitable zone defines a Goldilocks area for the possibility of life, various factors like the planet's atmosphere, star type, and orbital dynamics play essential roles in determining whether a planet within this zone can indeed support life. The Goldilocks zone, also known as the habitable zone, refers to the region around a star where conditions are just right for liquid water to exist on a planet's surface. The term Goldilocks draws from the fairy tale Goldilocks and the Three Bears, where Goldilocks finds that the porridge in one of the bowls is neither too hot nor too cold, but just right. Similarly, the Goldilocks zone around a star is not too hot and not too cold, it's just right for supporting conditions potentially conducive to life. The exact distance of the Goldilocks zone depends on the type of star in question. For a star like our Sun, a G-type main sequence star, the habitable zone typically ranges from about 0.95 to 1.4 astronomical units from the star, with 1 AU being the average distance between Earth and the Sun. Within this zone, a planet receives enough stellar radiation to maintain surface temperatures that allow liquid water to exist without boiling away or freezing solid. For stars that are cooler and less luminous than the Sun, such as M-type red dwarfs, the Goldilocks zone is much closer in. These stars emit less energy, so planets need to be nearer to receive sufficient warmth. For instance, the habitable zone around a red dwarf might range from just 0.1 to 0.3 AU. However, this proximity exposes planets to increased stellar activity, such as flares and radiation, which can pose challenges for the development of habitable conditions. Conversely, for stars that are hotter and more luminous, such as A-type or F-type stars, the habitable zone is farther out. These stars shine more brightly and emit more radiation, necessitating a greater distance to avoid overly intense heat. The habitable zone for such stars might extend from 1.5 to several AUs away. Several factors can influence whether a planet within the Goldilocks zone is genuinely habitable. A planet's atmosphere plays a critical role. A dense atmosphere rich in greenhouse gases like carbon dioxide can trap heat, effectively extending the habitable zone farther from the star. Conversely, a thin or absent atmosphere can render a planet too cold, even if it lies within the traditional bounds of the habitable zone. Moreover, the concept of the habitable zone doesn't account for subsurface environments, which can also harbor life. For example, moons like Europa and Enceladus in our own solar system lie far outside the Sun's Goldilocks zone, but possess subsurface oceans beneath their icy crusts, potentially heated by geothermal activity. Orbital characteristics like eccentricity also play a role. Planets with highly elliptical orbits experience significant temperature variations, which might complicate their habitability. Planets with nearly circular orbits are more likely to have stable, life-supporting climates. The Goldilocks zone is a crucial concept in astrobiology and planetary science, identifying the region around a star where liquid water can exist on a planet's surface, making it a key target in the search for life beyond Earth. The specific boundaries of this zone vary depending on the characteristics of the star and the planet in question, influenced by factors such as atmospheric composition and orbital dynamics. Despite its limitations, the Goldilocks zone remains a foundational guide for identifying potentially habitable exoplanets. Planetary magnetic fields play a significant role in contributing to habitability by providing protection against various space weather phenomena and maintaining the stability of a planet's atmosphere. These magnetic fields, generated by the movement of conducting materials within a planet's core, create magnetic shields that can deflect harmful solar and cosmic radiation, thereby fostering conditions conducive to life. One of the primary functions of a planetary magnetic field is to protect the atmosphere from being stripped away by solar wind. Solar wind is a stream of charged particles, mainly electrons and protons, emitted by the star. Without a magnetic field, these charged particles can gradually erode a planet's atmosphere as they collide with atmospheric particles and impart enough energy to eject them into space. Mars provides a striking example of what can happen when a planet loses its magnetic field. It is believed that Mars once had a thicker atmosphere, which was gradually eroded by solar wind after its magnetic field weakened, leading to the thin, arid atmosphere we observe today. The magnetic field also protects the planet's surface from harmful ultraviolet, UV, and cosmic radiation. High-energy particles can damage biological molecules, including DNA, thus jeopardizing the viability of potential life forms. On Earth, The magnetic field channels many of these charged particles towards the poles, where they interact with the atmosphere to create auroras, spectacular light displays. But more importantly, this deflection significantly reduces the radiation levels on the planet's surface, making it more hospitable for life. Additionally, a stable magnetic field can contribute to climate stability. Earth's magnetic field, for example, indirectly helps regulate the climate by protecting the ozone layer from solar wind erosion. The ozone layer acts as a shield against harmful UV radiation, which can otherwise lead to significant climatic and biological disruptions. By preserving the integrity of the atmosphere, including the ozone layer, the magnetic field supports stable and life-friendly climatic conditions. The presence of a magnetic field can also indicate a geologically active planet, which is another factor contributing to habitability. The dynamo effect, responsible for generating the magnetic field, requires a molten, convective outer core. This geological activity often correlates with other vital processes such as plate tectonics and volcanic activity, which recycle nutrients and contribute to long-term climatic stability through processes like the carbon-silicate cycle. However, magnetic fields aren't a strict requirement for life. Some moons in our solar system, such as Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, lack significant magnetic fields, but are still considered promising candidates for life due to their subsurface oceans, which may be heated by internal geological activity. These environments are shielded from radiation by their thick ice crusts, demonstrating that a magnetic field, while beneficial, is not the sole criterion for habitability. Planetary magnetic fields contribute significantly to habitability by protecting the atmosphere, reducing surface radiation, and supporting climate stability. They offer a shield against space weather and high-energy radiation, creating a safer environment for life to develop and thrive. Although not an absolute requirement for all forms of life, the presence of a magnetic field enhances the potential habitability of a planet and is a crucial consideration in the ongoing search for life beyond Earth. While Earth life is based on carbon, water, and oxygen, astrobiologists speculate about alternative biochemistries that could, in theory, support life in different environmental conditions. Some intriguing alternatives include silicon-based life forms, ammonium solvents, and exotic forms of biochemistry that do not rely on water. These hypotheses expand the possibilities of where life could exist beyond the traditional confines of our understanding. Silicon-based life. Silicon is often cited as a possible alternative to carbon because of its similar chemical properties. Both elements lie in the same group on the periodic table and can form 4 bonds with other atoms, allowing for complex molecular structures. Silicon-based biochemistry might occur in environments where temperatures are significantly higher than on Earth, as silicon-silicon and silicon-oxygen bonds are more stable at these temperatures. However, silicon dioxide, silica, is a solid at a wide range of temperatures, which could limit the mobility and versatility of silicon-based life. Still, in certain high-temperature environments, especially on planets or moons with thick silica-rich atmospheres, silicon life forms might be plausible. Ammonia-based life. Some scientists propose ammonia as a potential solvent for life because of its similarities to water. Ammonia has a lower freezing point, approximately -78°C, making it suitable for life in much colder environments than those on Earth. Like water, ammonia can dissolve many organic compounds and supports a variety of chemical reactions. It also forms hydrogen bonds, although they are weaker than those in water, which might affect the stability and structure of biological molecules. Planets or moons with abundant ammonia could support life that thrives at temperatures where water-based life would be frozen solid. Methane or ethane-based life. On Titan, Saturn's largest moon, there are lakes of liquid methane and ethane, suggesting the possibility of methane-based biochemistry. Methane and ethane could serve as solvents, and some scientists speculate about cryogenic life forms existing at extremely low temperatures, around -180°C, where methane and ethane are liquid. The metabolic processes in such life forms would need to be vastly different from those on Earth, as the energy yields from chemical reactions in hydrocarbons are typically lower than in water. Sulfur-based life. In environments rich in sulfur compounds, such as deep-sea hydrothermal vents on Earth, sulfur can play a central role in the metabolism of various extremophiles. Some microorganisms use hydrogen sulfide, H2S, in chemosynthesis, generating energy through chemical reactions that do not involve sunlight. A sulfur-based biochemistry might be plausible in similar extreme environments on other planets or moons, where sulfur compounds are abundant. Hydrocarbon solvents, liquid hydrocarbons such as those found on Titan, offer another potential solvent for alien life. Unlike water, hydrocarbons don't dissolve ionic substances well, so any hypothetical life relying on hydrocarbons would have to use non-polar biochemistry. This presents unique challenges and opportunities for how organisms might acquire and use nutrients, process waste, and store energy. Life, based on alternative biochemical pathways. It's also conceivable that life could use entirely different biochemical pathways than those observed in Earth life forms. For example, arsenic, typically toxic to Earth life, has been suggested as a potential alternative to phosphorus, a key element in DNA and ATP, although this is a matter of ongoing scientific debate. Extreme biochemistries, exotic environments such as high radiation zones, highly acidic or alkaline conditions, and high-pressure environments might support life forms based on biochemistries we can scarcely imagine. These might involve novel energy sources like radiation or electrical conductivity and unique metabolic cycles that recycle uncommon elements in ways that are foreign to Earth biology. While these alternative biochemistries remain speculative, they underscore the potential diversity of life in the universe. By considering these possibilities, scientists broaden the scope of astrobiological research, allowing for the exploration of environments previously deemed inhospitable. This inclusivity enhances our strategies for detecting extraterrestrial life, whether it be in our solar system or on exoplanets light years away. Our quest to understand the odds of intelligent life existing elsewhere in the universe brings us face to face with the enigmatic Drake equation. Conceived by the astronomer Frank Drake in the early 1960s, this formula compels us to consider several factors, including the number of stars forming each year in our galaxy, the fraction of those stars with planetary systems, and the number of planets per star capable of supporting life. Though each step involves speculative guesses, current estimates suggest that our galaxy, the Milky Way, harbors potentially billions of Earth-like planets situated in habitable zones where liquid water could persist. Recent advancements heighten this intrigue. The Kepler Space Telescope, launched in 2009, has detected nearly 3,000 confirmed exoplanets, some of which exhibit Earth-like conditions. Still, discovering microbial life is one matter. Intelligent civilizations capable of communication with us are another. The fraction of those planets where life evolves, the fraction where intelligent life develops, and the longevity of such civilizations all culminate in varied probabilities. Optimists might argue that given the universe's vastness, hosting about 100 billion galaxies, the odds tip favorably toward other intelligent beings. Skeptics concerned with the unknown terms in the Drake equation may view this pursuit with caution. Yet, every new discovery fuels our anticipation, leaving us wondering whether we are on the brink of contact or eternally alone in this cosmic ocean. Quantum mechanics is a branch of physics that delves into the behavior of particles at the smallest scales, such as atoms and subatomic particles. This fascinating field emerged in the early 20th century as scientists sought to understand phenomena that classical physics couldn't explain. At its heart, quantum mechanics reveals a world far removed from our everyday experiences, where particles can exist in multiple states at once, a concept known as superposition. For example, an electron isn't just in one place around an atom's nucleus, it exists in a probable cloud of locations until measured. Further intriguing is the phenomenon of entanglement, where particles become so deeply connected that the state of one instantaneously affects the state of another, no matter the distance separating them. A phenomenon Albert Einstein famously dubbed spooky action at a distance. These principles are encapsulated in Schrödinger's wave equation and Heisenberg's uncertainty principle, both cornerstones of quantum theory. Schrödinger's equation describes how the quantum state of a physical system changes over time, while the uncertainty principle highlights a fundamental limit to how precisely we can know both the position and momentum of a particle simultaneously. Though its principles might seem counterintuitive, quantum mechanics underpins many modern technologies, including semiconductors, lasers, and even MRI machines, illustrating its profound impact on both our understanding of the universe and practical advancements. Virtual particles are an extraordinary aspect of quantum mechanics, giving us a glimpse into the restless, fluctuating nature of what we often think of as empty space. Even in a vacuum, energy fluctuations incessantly create pairs of particles and antiparticles, which momentarily pop in and out of existence. These particles are called virtual because they don't adhere to the conserved energy and momentum laws that govern real particles. Instead, they exist transiently, permitted by the Heisenberg uncertainty principle, which allows for brief violations of energy conservation as long as they occur within incredibly short time frames. This puzzling phenomenon is often visualized through Feynman diagrams, which are schematic representations used to visualize interactions in quantum field theory. For example, in the context of the quantum vacuum, these diagrams illustrate how, for an infinitesimally small period, virtual particle pairs can emerge, interact, and then annihilate each other, returning their borrowed energy to the vacuum. This ephemeral dance of creation and annihilation has real-world implications. One such implication is the Casimir effect, where two uncharged metallic plates placed close together in a vacuum experience a force pulling them together. This force arises from the difference in the virtual particle's pressure between the plates and outside them, demonstrating that even empty space seethes with activity. These revelations underscore that a vacuum isn't truly empty, but teems with potentiality at the quantum level. Quantum foam, also known as space-time foam, is a concept rooted in the attempt to reconcile general relativity with quantum mechanics. Proposed by the theoretical physicist John Wheeler in the 1950s, it envisions space-time at the smallest scales as being turbulent and frothy rather than smooth and continuous. This notion arises from the Heisenberg uncertainty principle, which suggests that at scales on the order of the Planck length, approximately 10 circumflex 35 meters, energy fluctuations within a vacuum are so intense that they could momentarily warp space-time itself, creating a chaotic foam of tiny transient wormholes and bubbles. Imagine space-time not as a serene, placid lake, but as a stormy sea, where minuscule waves and ripples are constantly forming and dissolving. These fluctuations are a product of quantum gravitational effects, still largely theoretical, as our current technology cannot probe distances this infinitesimal. The concept of quantum foam serves as a bridge in our quest to understand the mysteries of quantum gravity, a realm where classical descriptions of gravity given by Einstein's general relativity and quantum mechanical principles must come together. As these microscopic distortions occur at the Planck scale, they hint at an intricate and dynamic structure of the fabric of the universe, challenging our macroscopic perceptions of space-time and offering tantalizing clues into the very nature of reality itself. Heisenberg's uncertainty principle is a cornerstone of quantum mechanics, establishing that certain pairs of properties, such as position and momentum, cannot be simultaneously known to arbitrary precision. This inherent uncertainty doesn't just limit our measurement capabilities, it fundamentally shapes the behavior of particles at quantum scales. This principle is intimately connected to the phenomenon of spontaneous creation, which is vividly manifested in the concept of virtual particles. According to the uncertainty principle, the product of the uncertainties in energy and time has a lower bound. This means that for exceedingly brief periods, the borrowed energy can be substantial. In a vacuum, where you might assume nothing exists, these energy fluctuations allow for the temporary creation of particle-antiparticle pairs. These virtual particles spontaneously pop into existence and then vanish back into the vacuum in a time span so fleeting that they do not violate the conservation of energy in any appreciable way. In this quantum dance, the uncertainty principle provides the wiggle room needed for these creations and annihilations to occur without violating the fundamental laws of physics. Thus, Heisenberg's uncertainty principle doesn't just impose limits, it also enables the restless dynamism of the quantum vacuum, allowing it to teem with ephemeral activity that might be invisible to us, but is essential in understanding the deeper, underlying mechanics of the universe. Vacuum energy plays a fascinating and crucial role in the realm of quantum mechanics, particularly in the phenomenon of particle creation. Contrary to the classical notion of a vacuum as an empty void, quantum mechanics reveals that a vacuum is a seething cauldron of energy fluctuations, even in the absence of any matter or radiation. This energy, sometimes referred to as zero-point energy, arises from the Heisenberg uncertainty principle, which implies that there can never be a state of absolute rest, even in what we perceive as empty space. These perpetual energy fluctuations in the vacuum give birth to pairs of virtual particles and antiparticles, which spontaneously emerge and then annihilate each other within incredibly brief moments. This temporary particle creation occurs because the vacuum energy provides the necessary energy to momentarily break the symmetries of space and time, allowing these particle pairs to exist. For example, in the phenomenon known as Hawking radiation, vacuum energy near the event horizon of a black hole can cause the creation of a particle-antiparticle pair, with one particle falling into the black hole while the other escapes, effectively leading to a loss of mass from the black hole itself. Moreover, vacuum energy is also implicated in the Casimir effect, where the vibrational modes of the quantum vacuum between two closely spaced metal plates result in an attractive force between them. This demonstrates that vacuum energy is not merely a theoretical construct, but has measurable physical consequences. Thus, vacuum energy underpins the creation of particles and influences macroscopic phenomena, painting a picture of the vacuum not as empty and inert, but as a dynamic and vital component of the quantum universe. Quantum fluctuations are fundamental to the birth of matter in the universe, serving as the ripples in the fabric of space-time that can eventually grow into the galaxies, stars, and planets we observe today. These fluctuations are tiny, random changes in energy occurring in a vacuum due to the Heisenberg uncertainty principle. During the very earliest moments of the universe, just fractions of a second after the Big Bang, the universe experienced inflation, a rapid expansion that stretched these minuscule fluctuations to macroscopic scales. As the universe expanded, these quantum fluctuations became the seeds for matter. The regions with slightly higher or lower energy densities eventually became gravitational wells that would attract more matter, leading to the formation of the vast cosmic structures we see now. This theoretical prediction aligns well with empirical observations. The cosmic microwave background, the afterglow of the Big Bang, provides a snapshot of the universe when it was just 380,000 years old. The tiny temperature variations in the CMB match the pattern expected from quantum fluctuations stretched by inflation, supporting the idea that these minute ripples were indeed the cradles of cosmic structure. Moreover, quantum fluctuations are continually at play at subatomic levels. These energy variations can manifest as particles and antiparticles that appear and disappear within the constraints of the uncertainty principle. Such fleeting particles can influence observable phenomena, such as the Casimir effect or Lamb shift, both of which have been confirmed experimentally. Thus, quantum fluctuations not only played a pivotal role in shaping the early universe and giving rise to matter, but they also continue to underpin many subtle yet significant physical phenomena. The idea that entire universes could spontaneously appear from quantum fluctuations is a topic of profound speculation and significant intrigue in theoretical physics. This concept stems from the framework of quantum cosmology, where our understanding of quantum mechanics is extended to the entire universe. According to one line of thought, based on the principles of quantum mechanics and general relativity, the universe could be part of a multiverse, a vast collection of potentially infinite universes with varying physical laws and constants. In the context of quantum fluctuations, the inflationary theory of the universe provides a fertile ground for such ideas. Inflation posits that a quantum fluctuation in the early universe could have led to an exponential expansion, stretching outwards to become an entire universe, much like our own. These quantum fluctuations could originate from the so-called false vacuum, a high-energy state that provides the conditions for inflation. Once the energy within this false vacuum decays, it could give rise to a bubble universe that expands rapidly and evolves into a cosmos with its own distinct properties. Support for the plausibility of these ideas comes from the theoretical framework known as the eternal inflation model. Here, inflation never entirely stops, but continues in different regions of spacetime, spawning new bubble universes endlessly. Each bubble represents a nascent universe with potentially different physical constants, laws, and structures, conceptually similar to quantum fluctuations on a grand cosmic scale. While these notions remain highly speculative and are far from being conclusively proven, they offer a tantalizing glimpse into the complex and mysterious possibilities suggested by quantum mechanics and cosmology combined. Current quantum theories, despite their success in describing the behavior of particles and forces at microscopic scales, face several significant limitations when it comes to explaining the creation of the universe and other large-scale phenomena. One of the most glaring limitations is the lack of a unified theory that seamlessly integrates quantum mechanics with general relativity, the theory of gravitation proposed by Albert Einstein. Quantum mechanics excels at describing the interactions of particles through the electromagnetic, weak, and strong nuclear forces, but it does not incorporate gravity effectively. This inconsistency becomes particularly problematic in extreme conditions, such as inside black holes or at the very beginning of the universe, where both quantum effects and gravity play crucial roles. Another limitation is the challenge of empirically testing concepts like quantum fluctuations giving rise to entire universes or the existence of a multiverse. These ideas, while mathematically intriguing, often lie beyond the reach of current experimental capabilities. Detecting or observing another universe spawned from quantum fluctuations remains a hypothetical endeavor due to the sheer scale and inaccessibility involved. Likewise, the foundational elements of quantum field theory and string theory, the latter being one of the leading candidates for a theory of everything, still lack experimental evidence to confirm many of their predictions about the early universe and high-energy phenomena. Moreover, quantum theories struggle to address the full nature of dark matter and dark energy, which comprise about 95% of the universe's total mass energy content. These mysterious components do not fit neatly into the standard model of particle physics, which is the current best framework for understanding fundamental particles and their interactions. Until we refine our quantum theories or discover new principles that can incorporate these enigmatic aspects of the universe, our understanding remains incomplete. The pursuit of quantum gravity and the hunt for empirical evidence to support far-reaching theoretical predictions remain on the cutting edge of modern physics, underscoring the current limitations and the exciting potential for future breakthroughs. Spontaneous symmetry breaking is a pivotal concept in the field of particle physics and cosmology, providing profound insights into the creation and diversity of particles in the universe. Essentially, spontaneous symmetry breaking occurs when a system that is symmetrical under certain conditions ends up in an asymmetric state. This process is fundamentally tied to the Higgs mechanism, which explains how particles acquire mass. To understand this, consider the early universe shortly after the Big Bang. In its initial extremely hot state, the universe likely possessed a high degree of symmetry with fields and forces unified. However, as the universe cooled, certain symmetries broke spontaneously, akin to how a perfectly round ball might settle into an asymmetric position when placed on top of a symmetrical hill. The Higgs field, a scalar field permeating all of space, underwent spontaneous symmetry breaking, leading to the emergence of the Higgs boson. The interaction of various particles with this Higgs field endows them with mass, distinguishing one particle from another based on how strongly each interacts with the field. In particle physics, this concept is elegantly captured within the framework of the Standard Model. Before symmetry breaking, fundamental particles were massless and indistinguishable under the unified force. Spontaneous symmetry breaking introduced distinctions that resulted in the varied particle zoo we observe today. Electrons, quarks, neutrinos, and more, all acquiring distinct masses and properties. This breaking also gave rise to different force carriers, such as the massive W and Z bosons responsible for weak interactions, and the massless photon responsible for electromagnetic interactions. Beyond the Standard Model, spontaneous symmetry breaking has implications for cosmology as well. In grand unified theories and models of inflation, spontaneous symmetry breaking can drive phase transitions in the early universe, leading to structures and forms that define cosmic evolution. Therefore, spontaneous symmetry breaking is not just a theoretical abstraction, but a fundamental process that underpins the intricate tapestry of particles and interactions, crafting the diverse universe we probe and explore today. Over the years, several key experiments have provided insights into the elusive realm of quantum fluctuations, validating theoretical predictions and enhancing our understanding of the quantum vacuum. One of the most direct ways to observe the effects of quantum fluctuations is through the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged, perfectly conducting plates placed very close together in a vacuum would experience an attractive force. This force arises because quantum fluctuations in the vacuum produce virtual particles, creating a pressure differential between the inside and outside of the plates. The Casimir effect was experimentally confirmed in the late 1990s by Stephen Lamoureux and others, demonstrating the tangible impact of quantum fluctuations. Another experimental avenue is the observation of the Lamb shift. This effect, first measured by Willis Lamb and Robert Rutherford in 1947, pertains to tiny shifts in the energy levels of electrons in hydrogen atoms. These shifts arise due to interactions with virtual particles generated by quantum fluctuations. The precise measurement of the Lamb shift provided crucial evidence in favor of quantum electrodynamics, the quantum field theory describing the interactions between charged particles and the electromagnetic field. Perhaps one of the most profound examples of quantum fluctuations at work is observed in the cosmic microwave background radiation, first detected by the COBE satellite in 1992 and more precisely by the WMAP and Planck spacecraft, is believed to be the imprints of quantum fluctuations from the very early universe, stretched to cosmic scales by inflation. These minuscule fluctuations in density seeded the formation of large-scale structures like galaxies and clusters, thus linking quantum mechanics with the grand architecture of the cosmos. In particle physics, high-energy experiments, such as those conducted at the Large Hadron Collider, frequently involve phenomena where quantum fluctuations play a significant role. Processes such as the creation of virtual particles contribute to the background noise in detectors, yet their consistent presence aligns with the predictions of quantum field theories. These experiments underscore the reality of quantum fluctuations, transforming theoretical concepts into observable phenomena. Even though we can't directly see these fluctuations, their effects are palpable in both microscopic and cosmic scales, asserting their importance in the framework of modern physics. The concept of zero energy in the universe, often discussed within the context of cosmology and theoretical physics, posits that the total energy of the universe might be zero when taking all forms into account. This intriguing notion springs from the interplay between positive energy, typically associated with matter and radiation, and negative energy, which is attributed to gravity. To elucidate, positive energy encompasses the energy stored in matter, having mass, and radiation, like photons. According to Einstein's famous equation, E equals mc squared, even a small amount of mass can represent a vast amount of energy. Similarly, the energy carried by radiation contributes to the overall positive energy content of the universe. On the other side of the ledger, the gravitational field contributes negative energy. In simplistic terms, because gravity is an attractive force pulling objects toward each other, it is said to possess negative potential energy. Imagine two masses separated by a distance. The work required to bring them together under gravity is considered positive, implying that potential energy prior to moving them must be negative to balance the equation. If we consider the universe as a whole, with large-scale structures like galaxies and clusters of galaxies, the negative gravitational energy resulting from their interactions could potentially offset the positive energy of matter and radiation. This balancing act suggests that the universe might obey a zero-energy principle. The sum of all positive energies, matter plus radiation, and all negative energies, gravitational, could net to zero. Some cosmological models, such as those considering the universe as a quantum fluctuation from a vacuum state, leverage this zero-energy hypothesis to explain the emergence of the universe without violating conservation laws. In these scenarios, the universe essentially borrows energy from the vacuum, balancing the books with negative gravitational energy. This zero-energy universe concept offers a tantalizing glimpse into the interplay of forces at cosmic scales and could provide clues to profound questions about the universe's origins and its ultimate fate. However, it remains a topic of intense debate and ongoing research, highlighting the intricate dance of forces that govern the cosmos. The notion that the total energy of the universe could be zero is one of the more mind-bending ideas in cosmology, suggesting a perfect balance between all forms of energy. This idea hinges on the interplay between positive and negative energies, primarily involving matter, radiation, and gravity. In the simplest terms, consider positive energy to be associated with all the matter and radiation in the universe. This positive energy includes the kinetic energy of moving particles, the energy stored in mass as per Einstein's equation E equals mc squared, and the energy carried by photons and other forms of electromagnetic radiation. If this were the whole story, the universe would indeed possess a vast amount of positive energy. However, gravity enters the equation with a twist. The gravitational field is considered to carry negative potential energy due to its attractive force. For instance, when two objects are moved apart against the gravitational pull, work must be done, which adds positive energy to the system. Conversely, the initial state before they were moved apart must embody negative potential energy to balance this out. Now, extending this idea to the entire universe, theoretical physicists propose that the negative gravitational energy could precisely counterbalance the positive energy associated with matter and radiation. Imagine the universe as a giant accounting ledger where every positive entry, like mass and radiation, is matched by a corresponding negative entry, gravitational potential energy. This conceptual framework supports models like the zero-energy universe hypothesis, where the universe emerged from a state of net zero energy. One fascinating implication of this idea is that it aligns with some interpretations of quantum mechanics and general relativity, suggesting the universe could arise from a quantum fluctuation from nothing, borrowing energy in a manner analogous to virtual particles in a vacuum. In these models, the initial inflationary period of the universe might have stretched these quantum fluctuations, leading to the mass and energy observed today, with the gravitational energy acting as a balancing force. Hence, despite the prodigious amount of energy we observe in the form of matter and radiation, the entire system's net energy could theoretically sum to zero. This concept is still subject to ongoing scrutiny and research, as it touches on deep questions about the nature of energy, gravity, and the origins of the cosmos. Nevertheless, it provides a profound and elegant perspective on the ultimate balance that might govern our universe. Gravitational energy plays a crucial role in the hypothesized balance of the universe's total energy, acting as the counterweight to the positive energy found in matter and radiation. This intriguing balance stems from the nature of gravitational potential energy, which is considered to be negative. To explain further, positive energy in the universe includes all forms of matter and radiation. Matter, as defined by E equals mc squared, stores vast amounts of energy in its mass. Similarly, various forms of radiation, including electromagnetic waves like light, carry substantial energy across the cosmos. In the absence of other factors, the universe might appear to be filled with an overwhelmingly positive energy tally. However, gravity adds a complexity to this equation. Gravitational potential energy is inherently negative because it describes an attractive force that pulls objects together. Imagine separating two masses in space. Doing so requires work, which adds positive energy to the system. Therefore, the initial state before separation must have contained negative energy to allow this addition to balance out. On a cosmic scale, this principle suggests that the cumulative gravitational potential energy from all masses in the universe could represent a significant reservoir of negative energy. Consider the gravitational interactions within galaxies, between galaxies, and across larger cosmic structures. Each of these interactions contains negative gravitational potential energy, representing the work required to overcome the gravitational forces pulling these massive objects together. In scenarios describing the universe as a zero-energy system, this negative gravitational energy perfectly offsets the positive energy from matter and radiation. This theoretical balance aligns with some concepts in quantum cosmology, where the universe could spontaneously emerge from a quantum fluctuation, borrowing energy in a zero-sum transaction. For instance, the inflationary model of the early universe posits that a rapid expansion phase stretched initial quantum fluctuations into macroscopic scales, establishing the large-scale structure of the cosmos. In this framework, positive energy from the hot, dense state of the Big Bang would be balanced by the negative gravitational energy, maintaining a net-zero energy state. The potential validity of this concept is still subject to investigation and debate among physicists, yet it offers an elegant perspective on the fundamental balances within our universe. Despite the vast complexities and energy evident in the cosmos, the idea that gravitational energy can act as a counterbalance underscores the profound and sometimes paradoxical nature of the laws governing reality. The law of conservation of energy is one of the most fundamental principles in physics, stating that energy cannot be created or destroyed, only transformed from one form to another. This principle holds true in every closed system within the universe, raising intriguing implications when we apply it to the universe as a whole. In the context of the cosmos, the concept of energy conservation can become considerably complex due to the nature of space-time itself and the dynamic evolution of the universe. For instance, when considering general relativity, energy conservation isn't as straightforward as in classical mechanics. General relativity, which describes gravity as the curvature of space-time, allows for the fabric of space to stretch, as seen during cosmic expansion. This stretching affects how we measure and account for energy on a universal scale. One significant challenge arises from the expansion of the universe, which itself is described by the metric expansion of space. As space expands, the energy density of matter and radiation changes. The energy of photons, for instance, decreases over time due to cosmological redshift, essentially the stretching of wavelengths as the universe grows. This loss of energy in photons due to redshift might seem paradoxical if taken literally, yet it aligns with general relativity's framework, where energy conservation isn't local but intertwined with the curvature and dynamics of space-time. Despite these complexities, the conservation principle may still find harmony within cosmological models through the concept of a zero-energy universe. According to this hypothesis, the positive energy from matter and radiation is exactly balanced by the negative gravitational energy, leading to a net energy sum of zero for the universe. This would imply that the universe as a closed system adheres to the conservation of energy in its totality, but does so in a nuanced and non-intuitive way that fits within the relativistic paradigm. Furthermore, the conservation of energy is central to the understanding of various processes in the universe, such as the formation of cosmic structures, the behavior of black holes, and the thermodynamics of stars. For instance, nuclear fusion in stars converts mass into energy, aligning with conservation principles while also adhering to Einstein's mass-energy equivalence. Thus, while the straightforward application of energy conservation in the universe is adjusted to accommodate the dynamics of general relativity and cosmic expansion, the underlying principle remains a cornerstone of our understanding. It reflects the universe's intricate balance and helps guide theoretical and empirical exploration into the fundamental laws that shape our cosmos. Virtual particles are a captivating phenomenon in quantum mechanics. They are particles that spontaneously pop in and out of existence, seemingly defying the classical laws of energy conservation. Unlike ordinary particles, virtual particles exist for such fleeting moments that they can never be directly observed. Instead, their presence is inferred through their effects on measurable quantities. These ephemeral manifestations arise due to the uncertainty principle, a cornerstone of quantum mechanics introduced by Werner Heisenberg, which allows for energy fluctuations in a vacuum over very short time periods. In a vacuum, the energy borrowed to create these particles is quickly repaid, thus maintaining the overall conservation of energy. Now, how do these ghostly entities tie into the concept of a zero-energy universe? The idea here is both as elegant as it is baffling. The zero-energy universe hypothesis suggests that the total amount of energy in the universe could actually sum to zero when considering both positive and negative contributions. In this framework, the positive energy of matter is perfectly counterbalanced by the negative energy of gravity. Virtual particles play a role in this cosmic balancing act, emerging briefly in the vacuum of space and contributing to the transient energy fluctuations. These fluctuations might even have been crucial in giving rise to the universe from nothing, as proposed by some cosmological models. Thus, virtual particles are not just quirks of the quantum realm, but are also integral to some of the profoundest theories about the very fabric of our universe. Calculating the energy of the universe is a meticulously challenging endeavor that intertwines concepts from both general relativity and quantum mechanics. One of the primary approaches involves understanding the contributions from various forms of energy, including matter, radiation, dark matter, and dark energy. Physicists start by measuring the contribution from ordinary matter, which comprises stars, planets, and galaxies. This luminous matter is relatively straightforward to quantify using telescopic observations and the gravitational effects it exerts. A more elusive form of energy, dark matter, does not emit light, but reveals its presence through gravitational interactions. Scientists estimate dark matter by observing rotational speeds of galaxies and gravitational lensing effects. On a grander scale, dark energy, which is theorized to drive the accelerated expansion of the universe, contributes significantly to the total energy budget. By measuring the rate of this cosmic expansion through supernova observations and combining this with the cosmic microwave background radiation data, physicists gain insights into the fraction of energy attributed to dark energy. Calculations also incorporate the theoretical groundwork laid by Einstein's equations of general relativity, which relate the curvature of spacetime to the energy content within it. When it comes to zero-energy universe theories, the calculations dip more into the interplay of these energies, balanced against the gravitational potential energy, aiming for a net energy that may approach zero. Hence, calculating the energy of the universe is not merely about adding up numbers, but requires a holistic understanding of cosmic forces, elements, and the very geometry of spacetime itself. The zero-energy universe theory, while intriguing, has certainly drawn its share of criticisms from the scientific community. One of the primary criticisms revolves around the difficulty in precisely defining and measuring gravitational potential energy in the context of an expanding universe. Unlike kinetic energy or mass energy, gravitational energy is inherently negative, but its calculation is complex and heavily dependent on the geometry of space-time, which can vary significantly on a cosmic scale. Critics point out that in an infinite and dynamically changing universe, keeping a tally on the exact balance of positive and negative energy becomes theoretically murky and may not be attainable with our current understanding and technological limitations. Another major point of contention is the speculative nature of some aspects of the theory. For instance, while the concept that the universe could emerge from fluctuations in a quantum vacuum is supported by some interpretations of quantum mechanics, direct empirical evidence for this precise mechanism remains elusive. Additionally, the theory assumes a uniform distribution and behavior of dark energy and dark matter, which are components that we currently do not fully understand. Our limited knowledge about these elusive elements, including their origins and properties, raises questions about the feasibility of accurately achieving a zero-energy balance. Consequently, while the zero-energy universe theory offers a fascinating and elegant framework, it remains heavily debated and is yet to be universally accepted within the scientific community. The zero-energy universe concept intriguingly aligns with principles of quantum mechanics, offering a compelling narrative that bridges microscopic quantum phenomena with the vastness of cosmological scales. In quantum mechanics, Heisenberg's uncertainty principle allows for the temporary violation of energy conservation through the existence of virtual particles, short-lived pairs of particles that spontaneously appear and then annihilate each other in a vacuum. This gives rise to the notion that, on incredibly short timescales, the laws of physics permit the borrowing of energy, provided it is repaid almost immediately. This quantum fluctuation is central to the zero-energy universe theory, suggesting that the universe itself could have originated from such a quantum event. In this theoretical framework, the positive energy of matter and radiation counterbalances the negative gravitational energy, leading to a net energy sum of zero. The holographic principle, which arises from quantum gravity theories, further enforces this idea by suggesting that all the information contained within a volume of space can be represented as encoded on its boundary, heavily implying a deep, fundamental connection between quantum mechanics and the structure of the universe. By adhering to the zero-energy constraint, the universe would be in line with the probabilistic nature of quantum mechanics, where the existence of something from nothing follows from quantum fluctuations. Thus, the zero-energy universe theory and quantum mechanics together propose a paradigm where the cosmos emerges as a natural consequence of the intrinsic, albeit temporary, uncertainties allowed in the quantum realm. The implications of a zero-energy universe for the creation of the universe are both profound and far-reaching, fundamentally altering our perception of cosmic genesis. One of the most striking consequences is the idea that the universe could have spontaneously arisen from quantum fluctuations in a vacuum, essentially from nothing. In quantum mechanics, the vacuum isn't empty, but is teeming with temporary fluctuating fields and particles. According to the zero-energy universe theory, these quantum fluctuations could give rise to the entire cosmos, with the positive energy of matter perfectly balancing the negative energy of gravity. If the total energy of the universe is indeed zero, then the creation of the universe doesn't violate conservation laws, making the emergence of everything from nothing an energetically feasible process. Furthermore, this concept could potentially unify aspects of quantum mechanics with general relativity, offering a coherent framework for the birth of the universe that fits within the known laws of physics. It provides a counter-narrative to traditional cosmological models, like the Big Bang singularity, suggesting that our universe's inception might not have required a unique singular event driven by unexplained initial conditions. Instead, the zero-energy hypothesis aligns with a naturally occurring process inherent in the quantum nature of the cosmos. Additionally, this theory might influence the way scientists approach the search for the initial conditions of the universe, encouraging the exploration of how quantum fluctuations could transition into large-scale structures observed today. Thus, the zero-energy universe concept provides a thought-provoking lens through which to consider the origins and ultimate fate of everything around us, seamlessly blending the microscopic and macroscopic realms into a unified narrative. Dark energy and dark matter play crucial roles in the zero-energy universe framework, acting as pivotal components that help balance the cosmic energy equation. Dark matter, which does not interact with electromagnetic forces and is hence invisible, contributes significantly to the universe's total energy. It is primarily inferred from its gravitational effects, such as the rotation curves of galaxies and gravitational lensing. Despite being elusive and undetectable directly, dark matter contributes positive energy to the universe, contributing to its total mass energy content. On the other hand, dark energy is even more enigmatic. Constituting roughly 70% of the universe's total energy density, dark energy is theorized to drive the accelerated expansion of the universe. It is usually characterized by a negative pressure, which theoretically results in negative gravitational energy due to its expansive effects on space-time. In the zero-energy framework, this negative gravitational energy from dark energy could counterbalance the positive energy contributed by both ordinary and dark matter. When we tally up all the energy contributions from ordinary matter, dark matter, radiation, and dark energy, the hypothesis suggests that these energies might sum to zero, maintaining an overall balance. Thus, dark energy and dark matter are not just mysterious elements, but are integral to the zero-energy universe concept, contributing to a delicate equilibrium that could explain the universe's emergence and sustained existence within the boundaries of known physical laws. The mathematical universe hypothesis, proposed by the cosmologist Max Tegmark, is a bold and intriguing idea that suggests the universe itself is a mathematical structure. According to this hypothesis, not only can the universe be described by mathematics, but it actually is mathematics. This idea stretches beyond the conventional view that math is merely a language or tool created by humans to describe the cosmos. Instead, Tegmark posits that every structure in the universe, from subatomic particles to galaxies, fundamentally arises from mathematical properties and relationships. In the mathematical universe hypothesis, reality is viewed as a vast and comprehensive mathematical object, composed of patterns, symmetries, and invariant quantities that are intrinsic to its existence. This means every physical entity or phenomenon can be represented as part of this mathematical structure. Under this model, what we perceive as physical existence is simply our interpretation of these underlying mathematical truths. If correct, this hypothesis has profound implications for our understanding of reality, suggesting that discovering the ultimate laws of physics is equivalent to uncovering mathematical truths. Tegmark's idea also implies that other universes, different from our own, could exist and be equally real, each governed by different mathematical structures. Thus, the mathematical universe hypothesis not only redefines what we consider to be physical reality, but also opens the door to an infinite set of possible universes, each potentially governed by its unique set of mathematical laws. The relationship between mathematical structures and physical reality has fascinated philosophers and scientists for centuries and remains a profound question at the core of the mathematical universe hypothesis. The concept posits that the physical universe and its behaviors are intrinsically tied to mathematical rules and constructs. Essentially, mathematical structures are abstract entities composed of numbers, shapes, probabilities, symmetries, and patterns. These structures govern the laws of nature, from the fundamental particles in quantum mechanics to the expansive patterns observed in cosmology. One striking example of this relationship is the predictive power of mathematics in describing physical phenomena. Equations like Newton's laws of motion, Einstein's theory of relativity, and Schrödinger's equation in quantum mechanics precisely predict the outcomes of experiments and observations. This uncanny accuracy suggests that the universe operates according to mathematical principles that we discover rather than invent. Furthermore, the mathematical language unifies disparate areas of physics. The same equations that describe the motion of planets also apply to the behavior of electrons in an atom, albeit with different parameters. The mathematical structures underlying symmetry, such as those described by group theory, play essential roles in describing the properties of elementary particles and forces. For instance, the standard model of particle physics relies heavily on the mathematics of symmetrical operations to categorize particles and predict their interactions. This model has yielded predictions confirmed by experimental data, further reinforcing the idea that physical reality is deeply rooted in and emergent from mathematical structures. Mathematical structures provide the blueprint for the laws of the universe. They not only describe, but also govern the physical phenomena we observe. This close relationship underscores the idea that to understand the universe fundamentally is to uncover the mathematics that lies at its core. Whether one subscribes to the mathematical universe hypothesis in full or not, it's clear that mathematics offers a profound and powerful lens through which to interpret the very fabric of reality. Mathematical structures that could potentially form universes span a diverse range of abstract concepts, each offering a unique set of properties and behaviors. Let's consider a few intriguing examples. One fundamental mathematical structure is the set of geometric shapes and spaces. Euclidean geometry, describing flat space, exists alongside non-Euclidean geometries, such as hyperbolic and elliptic geometries, which describe curved spaces. In a universe governed by hyperbolic geometry, for example, the rules of angles and distances are radically different, leading to distinctive cosmological and physical phenomena. Imagining a universe built upon such a geometric structure allows for intriguing possibilities, such as faster-than-light travel or unusual gravitational behaviors. Graph theory offers another fascinating mathematical framework. Graphs consist of nodes connected by edges and can represent a vast array of systems, from social networks to molecular structures. A universe based on graph theory could be fundamentally different from our continuous spacetime, potentially visualized as a vast network where nodes represent fundamental particles or quantum states, and edges represent interactions or relationships. This could lead to a discrete model of spacetime, where distances and motions are quantized, changing our understanding of continuity and causality. Algebraic structures, such as groups, rings, and fields, also present compelling possibilities. These structures define how elements combine and interact, which could inherently dictate the physical laws governing a universe. For example, a universe based on a particular group theory may have distinct symmetries that manifest as conservation laws or particle behaviors. Topology, which studies properties of space preserved under continuous deformations, suggests universes with different connectivity and boundary conditions. A universe with toroidal topology, resembling a donut shape, could enable closed loops and cyclical behaviors in space-time, leading to novel cosmological models. These examples illustrate that mathematical structures offer a rich tapestry of potential universes, each grounded in a unique set of properties and laws. As we explore these mathematical realms, we gain not only insights into the nature of our own universe, but also an appreciation for the endless possibilities that such abstract constructs can provide. The concept of a multiverse arises from mathematical principles in several profound and interrelated ways. One foundational aspect is the realization that the equations governing our universe do not uniquely specify a single set of initial conditions or parameters. Instead, these equations can describe an infinite variety of solutions, each corresponding to a different universe with potentially different physical laws and constants. For instance, the equations of general relativity allow for solutions that describe an array of different spacetime geometries, suggesting a multitude of possible universes with varying curvatures, energy densities, and even dimensional structures. Quantum mechanics further bolsters the multiverse idea through the interpretation that every quantum event branches off into a separate universe. This is most famously encapsulated in the many-worlds interpretation posited by Hugh Everett. According to this view, every possible outcome of a quantum measurement actually occurs, each in its distinct, non-communicating branch of the universe. The Hilbert space in quantum mechanics, representing all possible states, inherently supports this idea by mathematically encapsulating a vast landscape of potential universes. Inflationary cosmology is yet another fertile ground where mathematical principles lead to the multiverse concept. The inflationary model proposed by Alan Guth describes how a rapid exponential expansion of spacetime could give rise to pocket or bubble universes within a larger inflating multiverse. The equations governing this inflationary process indicate that different regions of space could stop inflating at different times, resulting in isolated universes with their own distinct properties and laws. This creates a mathematically grounded framework that naturally extends to a vast collection of universes. String theory, a leading candidate for a theory of everything, also implies the existence of a multiverse. String theory's complex equations allow for a multitude of solutions known as the string landscape. Each solution represents a different vacuum state with unique physical constants and dimensions. This landscape comprises an astronomical number of possible universes, each with its own laws of physics. The mathematical flexibility within string theory equations, therefore, inherently supports the existence of a multiverse. The multiverse concept is not merely a speculative idea, but is deeply rooted in the mathematical principles governing different areas of physics. From the diverse solutions of general relativity and quantum mechanics to the complex landscapes proposed by inflationary cosmology and string theory, mathematics consistently reveals a panorama of possible universes, each governed by unique laws and constants. This profoundly impacts our understanding of reality, suggesting that what we perceive as our universe might be just one of countless others in the grand mathematical tapestry of existence. Max Tegmark, a prominent cosmologist, proposed a framework for categorizing different types of multiverses, which he organized into 4 levels. Each level represents a progressively more inclusive and speculative notion of parallel universes, expanding our understanding of reality far beyond our observable universe. The first level, the Level 1 multiverse, consists of regions beyond the observable universe, but governed by the same physical laws and constants. Our cosmic horizon limits what we can see due to the finite speed of light and the age of the universe, but space itself extends far beyond this horizon. In this context, regions of space that are vastly separated from us might contain different arrangements of matter, leading to universes with different cosmic structures and histories. Essentially, these are universes separated by vast distances within an infinite space, but adhering to the same fundamental rules we observe. The second level, the Level 2 multiverse, stems from the theory of eternal inflation. In this scenario, the inflationary mechanism that caused the rapid expansion of our universe is not a one-time event, but continues eternally, creating pocket universes within the larger inflating space. Each pocket universe could have different physical constants, particle types, and even dimensions based on how symmetry breaking occurs during the inflationary phase. Thus, these universes could harbor entirely different physical laws than our own, resulting in a much more diverse multiverse. Going deeper into abstraction, the Level 3 multiverse arises from the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event that can happen does happen, but in separate branches of reality. Each of these branches constitutes a parallel universe, created when a quantum wave function collapses into various possible outcomes. This type of multiverse doesn't require separate spatial regions, but rather exists as a vast array of parallel realities where every conceivable outcome of every event occurs. Finally, the Level 4 multiverse is the most speculative and comprehensive. It is based on the idea that all mathematical structures correspond to physical realities. According to Tegmark, mathematical structures are not just abstract entities, but are as real as our physical universe. Thus, every mathematically possible universe exists, each with its own set of rules and fundamental definitions. This level encompasses all conceivable universes described by different mathematical frameworks, suggesting an incredibly vast and all-encompassing multiverse. Tegmark's 4 levels provide a structured way to think about the concept of parallel universes, moving from the relatively familiar ideas of vast spatial separations to the profound and abstract notion that all possible mathematical realities exist. This framework expands our understanding of what universe could mean, challenging the boundaries of science and philosophy alike. Symmetry is a fundamental concept in both mathematics and physics, playing a crucial role in the formulation and understanding of the mathematical multiverse. In this context, symmetry refers to invariance under certain transformations, which can include spatial rotations, reflections, translations, and more abstract operations. These symmetrical properties are not merely aesthetic or simplifying tools, but are deeply ingrained in the laws governing physical systems and mathematical structures. In the mathematical multiverse, symmetry often dictates the fundamental laws and constants that define a particular universe. For example, the standard model of particle physics, which accurately describes the forces and particles in our universe, is built on specific symmetrical properties encapsulated by group theory. These symmetries determine how particles interact, ensuring the conservation of certain quantities like energy, momentum, and charge. Different universes within the mathematical multiverse might be governed by different symmetry groups, leading to varied sets of physical laws and constants. For instance, a universe dictated by a different symmetry group might have different types of fundamental particles or forces, resulting in entirely unique physical properties. Moreover, symmetry breaking, a process where a system that is initially symmetrical becomes asymmetrical under certain conditions, plays a significant role in the formation of diverse universes within the multiverse. During events like spontaneous symmetry breaking, the universe transitions from a high symmetry state to a lower symmetry state, leading to differentiated structures and phenomena. In our universe, this process is crucial for understanding the early moments after the Big Bang, where symmetrical forces split into the distinct forces we observe today. Different instances of symmetry breaking could lead to vastly different universes, each with its unique set of physical laws. At a more abstract level, mathematical structures that form the basis of Tegmark's Level 4 multiverse are inherently symmetrical. These structures often possess symmetries that define their intrinsic properties and behaviors. For example, geometric spaces can exhibit various symmetries like rotational or translational invariance, each leading to different types of spatial geometries. In a multiverse composed of different mathematical structures, the symmetries of each structure would play a pivotal role in defining the corresponding universe's nature. Symmetry also facilitates the unification of seemingly disparate physical phenomena through a single, coherent mathematical framework. For instance, Noether's theorem, one of the cornerstones of theoretical physics, links symmetries directly to conservation laws. In a mathematical multiverse, such unifying principles suggest that the diverse tapestry of possible universes might still adhere to deeper, universal symmetrical principles, albeit realized in different ways. Symmetry in the mathematical multiverse is more than just a helpful concept. It is a foundational principle that can determine the properties, behaviors, and fundamental laws of individual universes. Different symmetrical properties and symmetry-breaking events give rise to the rich diversity of universes within the multiverse, each governed by unique but mathematically consistent rules. The relationship between mathematics and the laws of physics is both profound and intricate, serving as a foundational bedrock for our understanding of the universe. Mathematics provides the language and framework through which the laws of physics are articulated and understood, acting as the bridge between abstract theoretical constructs and empirical observations. One of the most compelling aspects of this relationship is the predictive power that mathematics affords. Physical laws, when expressed mathematically, enable precise predictions about the behavior of natural systems. For example, Newton's laws of motion and universal gravitation are captured by straightforward mathematical formulas that can predict the trajectory of planets, the fall of objects, and much more. Similarly, Einstein's equations of general relativity, which describe the curvature of spacetime in response to mass and energy, have led to predictions verified through phenomena such as gravitational lensing and the expansion of the universe. Mathematics also provides a unifying framework that links disparate physical phenomena under a single coherent set of principles. Maxwell's equations are a prime example of this unification, elegantly combining the laws of electricity and magnetism into a single cohesive framework. In the realm of quantum mechanics, Schrödinger's equation governs the behavior of particles at microscopic scales, revealing a probabilistic nature fundamentally described by wave functions. Moreover, the intrinsic symmetry found in many physical laws is inherently mathematical. Group theory, a branch of mathematics exploring symmetrical structures, plays a crucial role in modern physics. It underpins the standard model of particle physics, explaining how forces and particles are interconnected. Emmy Noether's theorem formalizes this relationship by linking symmetries in physical systems to conservation laws, such as the conservation of energy and momentum, revealing an intimate connection between physical invariances and mathematical symmetries. The relationship extends even further into the realm of theoretical physics. Concepts such as string theory rely heavily on advanced mathematics to propose that fundamental particles are not point-like, but rather one-dimensional strings whose vibrations determine particle properties. These models often exist in higher dimensional spaces, necessitating complex mathematical frameworks like differential geometry and topology to describe potential cosmological and quantum phenomena. Additionally, the discovery of mathematical truths often precedes their physical application, a phenomenon that has repeated throughout history. Non-Euclidean geometries were studied as pure mathematics long before Einstein found that they perfectly described the curved space-time in general relativity. Such instances suggest that mathematics has an intrinsic capability to elucidate the underlying structure of physical reality, sometimes anticipating scientific discoveries by decades or even centuries. The relationship between mathematics and the laws of physics is deeply intertwined. Mathematics provides the fundamental language for formulating physical laws, predicting natural events, and unifying diverse phenomena. Whether through the precise descriptions of dynamics and forces or the more abstract constructs in theoretical frameworks, mathematics and physics work in concert to deepen our understanding of the universe. This symbiotic relationship suggests that the universe itself may be fundamentally mathematical in nature, a concept that underpins many speculative and theoretical explorations in modern science. Different mathematical models can lead to the concept of different universes by describing alternative sets of physical laws, constants, and parameters that result in varied possibilities of how a universe can evolve and behave. Each mathematical model encapsulates a distinct framework of rules and relationships, fundamentally shaping the nature of everything within that universe, from fundamental particles to the large-scale structure of space-time itself. Here's how this divergence can manifest. Firstly, consider the role of geometry in shaping different universes. The properties of space itself, whether it is Euclidean, flat, hyperbolic, saddle-shaped, or elliptic, spherical, determine how matter and energy interact within it. For instance, Einstein's theory of general relativity describes our universe using Riemannian geometry, a type of non-Euclidean geometry. This model allows for curved spacetime, which is essential for explaining the phenomena of gravity. If a different type of geometry were used, such as one with a different curvature or dimensionality, the resultant universe would have different gravitational behaviors, potentially leading to entirely different cosmic structures and phenomena. Another example is seen in the context of quantum mechanics and statistical models. Schrödinger's equation, which governs the behavior of quantum systems, implies certain probabilities and outcomes for particle behavior. However, different mathematical formulations, such as those seen in alternative interpretations of quantum mechanics, for example, pilot wave theory or objective collapse models, could lead to universes where quantum events unfold in radically different ways. These variations can influence everything from atomic structures to the fundamental nature of randomness and determinism in these universes. Symmetry and its breaking is another domain where mathematical models lead to diverse universes. The standard model of particle physics relies on specific symmetry groups, like SU3 cross SU2 cross U1, to describe particle interactions and forces. If a universe were based on different symmetry groups, the types of elementary particles, the forces acting upon them, and their interplay would all differ. For example, a universe operating under a different gauge group might feature a different number of fundamental forces or particles with dissimilar properties, leading to a very different set of physical phenomena. Mathematical constants also provide a fertile ground for diversity. Parameters such as the gravitational constant, the speed of light, and Planck's constant define much about the behavior of physical systems. Universes where these constants take on different values could have dramatically different laws of physics. For instance, a slightly higher or lower gravitational constant would affect star formation, planetary orbits, and even the expansion rate of the universe, leading to a cosmos with distinct evolutionary paths and structures. In the realm of higher theoretical models like string theory, mathematical models proposed by different configurations of strings, branes, and compactified dimensions can lead to a multitude of vacua, or possible states of the universe. These vacua represent different solutions to the string theory equations, each corresponding to a unique set of physical laws and constants. This allows for a vast landscape of potential universes, each with its own unique characteristics based on the specific mathematical formulation at play. The mathematical multiverse suggests a radical shift in our understanding of reality. Traditionally, we consider what is real to be what we can observe and measure in our universe. However, if every conceivable mathematical structure corresponds to its universe, the scope of what is real expands vastly beyond our observable cosmos. This broadens the notion of existence itself, implying that reality might not be singular but a vast collection of equally real universes, each governed by different mathematical laws and principles. Such a view challenges ontological perspectives and invites us to consider a more pluralistic notion of existence. Epistemologically, this concept questions the limits of human knowledge and understanding. If there are infinitely many universes, each with different sets of physical laws and constants, understanding our specific universe could be seen as a local endeavor within a much larger, possibly unknowable context. This raises questions about the nature and scope of scientific inquiry. Are there universal truths, or are our scientific laws just one set of rules among many? It challenges the idea that the laws we discover are unique, instead suggesting they are contingent on our specific mathematical framework. Moreover, the mathematical multiverse has significant implications for the concept of fine-tuning and the anthropic principle. The fine-tuning argument posits that the constants of our universe appear precisely calibrated to allow for the existence of life, particularly intelligent life. A multiverse filled with all possible mathematical universes dilutes this argument. If every possible set of constants exists, it is not surprising that at least one universe like ours has the properties necessary for life. This shifts the reasoning from a special, possibly designed cosmos to a natural consequence of infinite diversity. Ethically and existentially, the multiverse theory has implications for the meaning and significance of human life. If our universe is just one among an infinite number of universes, each with its unique trajectories and outcomes, what does this mean for individual existence? This can be both humbling and liberating. Humbling in the sense that our universe and our individual lives are not unique in the grand scheme, yet liberating in the sense that every possibility is realized somewhere in the multiverse. Additionally, the the mathematical multiverse touches on the nature of mathematical Platonism, the philosophical view that mathematical entities exist independently of human thought. If every mathematical structure has a physical counterpart, it suggests a deeply Platonic reality where abstract mathematics is more than a human invention, but an intrinsic part of the fabric of all possible universes. This has implications for the philosophy of mathematics, reinforcing the idea that mathematical discovery is akin to uncovering fundamental truths about a broader, multiversal reality. Imagine for a moment that our universe is just one of countless mathematical structures existing within a vast multiverse. Each of these structures follows its own set of mathematical rules and principles, creating entirely self-consistent worlds. According to cosmologist Max Tegmark's hypothesis, known as the mathematical universe hypothesis, these mathematical structures exist in a Platonic sense. Here's where it gets truly fascinating. If each mathematical universe is entirely self-contained, operating under its own unique laws, how could they ever interact? The idea of interaction between mathematical universes suggests a bridge that transcends their inherent isolation. Consider the concept of quantum entanglement, where particles remain interconnected regardless of the distance separating them. Some theorists speculate that an analogous form of entanglement might exist between separate mathematical realities. This interaction wouldn't necessarily mean a direct exchange of particles or energy, as we understand in our own universe. Instead, it might involve a more abstract form of information exchange or interference. If mathematical universes could influence each other in any perceivable way, it would revolutionize our comprehension of reality, suggesting a complex meta-reality where these different realms are somehow woven together into the fabric of the cosmos. One of the most compelling arguments for the existence of a divine creator is the fine-tuning of the universe. Proponents of this argument point out that certain fundamental physical constants and conditions are extraordinarily precise, allowing for the existence of life as we know it. If the gravitational constant, the strength of electromagnetic interactions, or the rate of expansion of the universe were even slightly different, stars might never form, and life could be impossible. This precision often leads to the question, did these constants arise by chance, or were they set intentionally by a higher intelligence? Many argue the likelihood of chance is so infinitely small that an intelligent designer seems not just plausible, but necessary. Another major argument is the cosmological argument, particularly the Kalam cosmological argument, which hinges on the principle of causality. It asserts that everything that begins to exist has a cause, making the universe, which began with the Big Bang around 13.8 billion years ago, no exception. This line of reasoning leads to the conclusion that the universe must have a cause that exists outside space and time. For many, this cause is best explained as a divine creator, an entity with the power to bring not just matter but the very fabric of space-time into existence. This argument dovetails with the philosophical musings of Aristotle and Aquinas, who posited a first mover or necessary being, fundamentally grounding the continuous existence and progression of everything. In Christianity, the creation of the universe is a central theme, described vividly in the book of Genesis. According to the Judeo-Christian tradition, God created the heavens and the earth in 6 days and rested on the seventh. The process includes the creation of light, separating it from darkness, forming the sky, land, and sea, and populating the world with plants, animals, and finally humans. This narrative underscores a purposeful, sequential divine act characterized by an omnipotent and benevolent creator. The Genesis account, while often interpreted literally by some, is also viewed allegorically by others, who see it as expressing fundamental truths about the divine origin of the cosmos, life's inherent order, and humanity's unique place in the creation. In Hinduism, the concept of creation is more cyclical than linear. The universe is said to go through endless cycles of creation, preservation, and destruction, known as yugas. According to Hindu cosmology, the god Brahma is the creator who brings the universe into being. Vishnu, the preserver, maintains it, while Shiva, the destroyer, dissolves it, allowing for rebirth. The Rig Veda, one of Hinduism's oldest sacred texts, speaks of a primordial cosmic being, Purusha, whose self-sacrifice led to the creation of the world. Additionally, Hindu mythology includes various creation stories like that of the cosmic ocean churned by gods and demons to produce the nectar of immortality, which reveals a rich symbolic tapestry about the universe's origins. In both religious traditions, and others such as Islam and Buddhism, creation stories provide profound insights into how different cultures understand the cosmos, our place within it, and the divine forces believed to orchestrate it all. The Quran, for instance, presents a vision of a universe created by Allah, unfolding systematically from a state of gaseous darkness to an ordered world, emphasizing divine omnipotence and unity. Comparatively, Buddhist cosmology isn't centered on creation by a deity, but rather on cycles of existence shaped by karma and cosmic law, reflecting a worldview where the universe's structure is an eternal, dynamic process rather than a finite act of creation. Each explanation offers a unique lens through which believers see their existence, the universe's nature, and the divine or metaphysical realities that sustain it. The concept of a first cause largely stems from philosophical and theological contemplation on the origin of the universe. It's the idea that everything in existence has a cause, and if you trace these causes back far enough, you must arrive at an initial uncaused cause that set everything else into motion. This first cause is often equated with a divine creator or a prime mover, an ultimate source from which all things emanate. Philosophers and theologians like Aristotle and Thomas Aquinas have famously expounded on this concept. Aristotle spoke of an unmoved mover, a perfect being whose very existence is the cause of all other movement and change in the universe. For Aristotle, this mover is eternal, unchanging, and entirely actualized, meaning it lacks any potential for change, as it is already perfect. Aquinas, building upon Aristotle's ideas, formulated the 5 ways in his Summa Theologica, arguing that the chain of causes must logically lead to a first cause, which everyone understands to be God. Aquinas' argument is rooted in the impossibility of an infinite regress of causes, suggesting that without a first cause, nothing could exist today. The first cause concept is not confined to Western thought. In various Eastern philosophies and religious systems, there's also recognition of an ultimate source or principle that sparks existence, even if it isn't personified as in monotheistic traditions. For example, in Hinduism, Brahman is considered the ultimate reality or cosmic spirit, from which the universe stems, while in some interpretations of Buddhism, it's acknowledged that the fabric of causality must have an ultimate source. This concept intersects with modern cosmology as well. The Big Bang theory describes a moment around 13.8 billion years ago when the universe rapidly expanded from an extremely hot and dense singularity. Some argue that the initial conditions of the Big Bang could point to a first cause, though others posit that our understanding of physics at that singularity might be incomplete. Whether conceived through the lens of religion, philosophy, or science, the concept of a first cause continues to provoke deep reflection and debate about the ultimate origin of everything. The cosmological argument is a classical philosophical and theological rationale that seeks to establish the existence of a divine creator based on the existence and origins of the universe. It primarily hinges on the principle of causality, which asserts that every effect must have a cause. The argument is crafted to show that the existence of the universe, which is an effect, must ultimately trace back to a cause that itself is uncaused. This uncaused cause is posited to be a divine creator. One of the most prominent forms of the cosmological argument is the Kalam cosmological argument, which consists of a few simple premises. Everything that begins to exist has a cause. The universe began to exist. Therefore, the universe must have a cause. The strength of this argument lies in its logical progression, leading to the conclusion that if the universe had a beginning, as suggested by evidence like the Big Bang theory, it must have a cause beyond itself. Given that the universe encompasses all of space and time, this initiatory cause must inherently exist outside of space and time, suggesting an immaterial, timeless, and powerful entity, attributes commonly associated with a divine creator. Another variation is Thomas Aquinas' argument from contingency. Aquinas posited that everything in the universe exists contingently, meaning it could conceivably not exist, as its existence depends on external factors. If everything were contingent, there could have been a time when nothing existed, and nothing would exist now, as nothing can come from nothing. Therefore, there must be at least one necessary being whose existence is not contingent upon anything else, but is inherent and eternal. This necessary being, which grounds the existence of all contingent realities, is identified with God. Together, these arguments make a case for a divine creator by pointing to the necessity of a first cause or an unconditioned reality to account for the existence and nature of everything in our universe. They assert that the very fact of the universe's existence is most coherently and plausibly explained by the presence of a divine creator, one that initiates and sustains all being and becoming. The fine-tuning argument for a supreme creator posits that the precise conditions necessary for life in the universe are so improbably specific that they suggest intentional design. While this argument is rooted in the seemingly improbable nature of these conditions, it aims to provide evidence of a purposeful creator who set these conditions with the intent of fostering life. Consider the fundamental forces of nature: the gravitational constant, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Each of these forces must lie within an extraordinarily narrow range for a universe capable of supporting life. For instance, if the gravitational constant were even slightly stronger or weaker, the universe could have either collapsed back on itself or expanded too quickly for galaxies, stars, and planets to form. Similarly, the balance between the strengths of the strong and weak nuclear forces affects the formation of the basic elements necessary for life. These parameters, among dozens of others, must be finely tuned to a degree that is statistically mind-boggling to allow for a cosmos where life as we know it can exist. Supporters of the fine-tuning argument often compare these cosmic parameters to the idea of a lottery with odds so slim they defy comprehension. The sheer improbability of a life-permitting universe arising by mere chance leads some to conclude that it points to an intelligent designer. This designer is perceived as setting the dials of the universe's laws and constants meticulously to ensure a hospitable environment for life. One famous exponent of fine-tuning, physicist John Polkinghorne, has argued that the beauty and order seen in the mathematical laws of physics suggest a mind behind the cosmos. Likewise, philosophers like Robin Collins contend that the fine-tuning argument adds substantial weight to the case for a supreme creator, a being that purposefully calibrated the universe to make life possible. While alternative explanations such as the multiverse hypothesis exist, positing countless universes with varying laws where our universe just happens to be one that supports life. Proponents of the fine-tuning argument argue that a divine creator remains the more plausible and elegant solution to this profound cosmic order. Theologians often approach the reconciliation of scientific theories with divine creation through a variety of frameworks that emphasize compatibility rather than conflict. One prominent approach is the concept of theistic evolution, which posits that evolutionary processes described by science are the means through which a divine creator brings about life. This perspective allows for acceptance of biological evolution and geological timescales, viewing them as mechanisms orchestrated by God. In this view, the natural processes uncovered by science are not seen as contradictory to divine action, but rather as expressions of it. By integrating scientific understanding with theological doctrine, theistic evolutionists maintain that the grandeur and complexity of the natural world are evidence of divine wisdom and power. Moreover, theologians like John Polkinghorne and Francis Collins, both of whom are also scientists, argue that scientific discoveries and religious beliefs address different dimensions of the same reality. Polkinghorne, for instance, uses the term complementarity to describe the relationship between science and religion. Each offers its own perspective on truth. While science explains the mechanisms of the universe, such as the Big Bang or evolutionary theory, religion addresses the meaning and purpose behind these processes. This perspective is not about filling gaps in scientific knowledge with divine intervention, but about seeing the divine hand in the known processes. Another reconciliation approach is the interpretative flexibility of sacred texts. Many theologians advocate for reading the biblical creation accounts in a non-literal, allegorical, or metaphorical way. For example, The 6 days of creation described in Genesis can be understood as symbolic of longer periods, aligning with the scientific evidence of a universe that is around 13.8 billion years old. This symbolic interpretation allows theologians to maintain the theological truths of creation, such as the belief in a purposeful, divinely guided origin of the universe, while embracing the empirical findings of contemporary science. Additionally, the principle of contingency provides a synthesis between divine creation and scientific discovery. This principle holds that the laws of nature and the constants of the universe could have been otherwise, which raises the question of why they are such that life is possible. From a theological standpoint, the contingent nature of the universe points to a divine creator who chose to create the cosmos in this particular life-permitting way, suggesting a deliberate act of creation that is harmonious with the scientific understanding of the universe's constitution and history. Through these various approaches, theologians seek to construct a coherent worldview that honors both the empirical rigor of science and the spiritual insights of theology. This integrated perspective aims to enrich understanding of the universe by acknowledging the roles of both divine purpose and natural processes. Philosophical objections to the concept of a divine creator are numerous and varied, often arising from different metaphysical, epistemological, and ethical perspectives. One of the most significant objections is rooted in the problem of evil. This argument, famously articulated by philosophers like David Hume and J.L. Mackie, questions how an omnipotent, omniscient, and omnibenevolent God could allow the existence of evil and suffering. If a divine creator has the power to prevent suffering and the knowledge of all suffering but chooses not to, it raises significant doubts about either the nature or the existence of such a being. The prevalence and intensity of both natural and moral evils in the world challenge the coherence of traditional theistic attributes. Another crucial objection comes from the realm of empiricism and the principle of parsimony, often associated with the philosopher David Hume and later formalized as Occam's razor. This principle recommends that when presented with competing hypotheses, one should select the one that makes the fewest assumptions. Many philosophers and scientists argue that naturalistic explanations for the universe, which rely on observable phenomena and well-established scientific principles, are simpler and more parsimonious than invoking a supernatural divine creator. They contend that hypotheses about a divine creator introduce unnecessary complexities without providing additional explanatory power beyond what science already offers about the origins and workings of the universe. Additionally, the issue of the infinite regress in the cosmological argument presents another philosophical challenge. Critics argue that proposing a divine creator as the first cause simply relocates the problem rather than solving it. If everything needs a cause, then why would the divine creator itself be exempt from this requirement? The question, who created God, leads to an infinite regress unless one accepts the special pleading that a divine creator is necessary and uncaused. This special status is often seen by skeptics as a conceptual weakness that undermines the cosmological argument's appeal. Lastly, some objections arise from the perspective of non-theistic existentialism, a philosophical stance advanced by thinkers like Jean-Paul Sartre and Friedrich Nietzsche. This viewpoint challenges the necessity and desirability of a divine creator in providing meaning and purpose to life. Sartre, for example, argued that individuals should find their own purpose and create meaning through their choices, actions, and relationships, rather than relying on an external divine entity. This existential autonomy fosters a human-centered approach to ethics and meaning, often clashing with the idea of a preordained purpose imposed by a deity. These philosophical objections converge to challenge the coherence, necessity, and implications of the concept of a divine creator, fostering ongoing debate and exploration in both philosophical and theological circles. The problem of evil is one of the most challenging philosophical and theological issues in relation to the concept of a divine creator. It questions how an all-powerful, all-knowing, and all-good deity would allow the existence of evil and suffering in the world. This dilemma is articulated through both logical and evidential forms, each presenting nuanced critiques of the coherence of traditional theism. The logical problem of evil, famously presented by philosophers such as Epicurus and more formally by J.L. Mackie, argues that the existence of evil logically contradicts the characteristics commonly attributed to a divine creator. The argument goes as follows. If God is omnipotent, God has the power to eliminate all evil. If God is omniscient, God knows about all the evils and their potential consequences. If God is omnibenevolent, God would want to eliminate all evil to prevent suffering. However, evil exists. Therefore, the existence of such a God appears logically inconsistent with the existence of evil. This formulation pushes theists to either redefine the nature of God or provide a framework in which the coexistence of God and evil is logically possible. In response to the logical problem, many theists propose the free will defense, most notably articulated by Alvin Plantinga. This defense suggests that God grants human beings free will, which is a greater good that justifies the possibility of moral evil. Free will allows for genuine relationships and moral growth, but it also permits individuals to choose evil actions. Thus, the existence of evil is a necessary consequence of a world where free will is granted by a divine creator, preserving the notion of God's omnipotence, omniscience, and omnibenevolence. The evidential problem of evil, advanced by philosophers like William Rowe, takes a different approach. It argues that while the existence of some evil might be compatible with a divine creator, the sheer amount and apparent gratuitousness of suffering seem unlikely in a world governed by an all-good deity. This argument does not claim a logical contradiction, but instead questions the probability that an omnipotent and omnibenevolent God would allow so much seemingly pointless suffering. Instances of intense and widespread suffering, such as natural disasters or the suffering of innocent children, are presented as evidence that challenges the likelihood of such a deity existing. In addressing the evidential problem, some theologians invoke the concept of soul-making, a theory proposed by John Hick. This theodicy suggests that the world with its challenges and sufferings is a setting for spiritual growth and development. The idea is that experiencing and overcoming suffering can lead to personal and collective moral improvement, and that this process is ultimately aligned with divine purposes, even if it is not immediately apparent to human understanding. Additionally, other theodicies explore the idea that human knowledge is limited, and what appears as gratuitous suffering might have reasons beyond human comprehension, often referred to as skeptical theism. This perspective posits that trusting in the greater wisdom and benevolence of God can be a rational stance, even in the face of apparently inexplicable evils. The problem of evil thus remains a profound and complex issue for the concept of a divine creator, fostering deep philosophical and theological inquiry into the nature of divinity, free will, moral growth, and the limits of human understanding. Creation myths from different cultures offer fascinating insights into how diverse societies have tried to understand the origins of the universe and human existence. Despite their varied geographical and historical contexts, many of these myths share certain themes and structures that reflect humanity's universal quest for meaning and explanation. In the Judeo-Christian tradition as found in the Book of Genesis, the universe is brought into being by a single, omnipotent God. Over 6 days, God creates light, sky, land, vegetation, celestial bodies, birds, fish, animals, and finally human beings, culminating in a day of rest. This narrative emphasizes the power, intentionality, and benevolence of a singular divine creator, setting a foundational framework for the Abrahamic religions. By contrast, Chinese cosmological narratives, such as the story of Pangu, present a more animistic and anthropomorphic view of creation. In this myth, Pangu emerges from a cosmic egg, separating the chaos within into the heavens and the earth through his own physical transformation. His death gives rise to various natural elements, symbolizing an intimate connection between the creator and the created world. This concept underscores a unity within creation processes, stressing the interdependence and holistic nature of all things. Moving to the Polynesian cultural sphere, the Hawaiian creation chant Kumulipo provides another unique perspective. This chant is a genealogical prayer that traces the origins of the cosmos through a series of generations, depicting the emergence of life forms from primordial darkness. It highlights a genealogical and evolutionary view of creation, where gods and natural elements are deeply interrelated. It emphasizes the idea that all life forms, including humans, are interconnected parts of a continuous creation story. Similarly rich is the Hindu creation story from the Rig Veda, which speaks of a primordial cosmic being, Purusha, whose sacrifice leads to the creation of the world. His body parts become different elements of the universe, deities, and social classes. This sacrificial act reflects themes of unity, transformation, and cyclical processes, consistent with Hindu cosmology's broader metaphysical principles that emphasize cycles of creation, preservation, and destruction. In indigenous American traditions, such as the Navajo creation story, there's often a communal aspect to creation. The Navajo myth describes a series of worlds through which ancestors must journey, each world representing a stage of spiritual and physical development. This narrative places significant emphasis on the journey, transformation, and the collective effort of beings working together to create and sustain life, embodying a communal and process-oriented view of existence. The Nordic creation myth provides yet another strikingly different image. In Norse mythology, the world emerges from the icy void of Ginnungagap, where the fires of Muspelheim meet the cold of Niflheim. From this dynamic interaction, the first giant Ymir is born, and from Ymir's body, the gods Odin and his brothers fashion the earth. This myth highlights conflict, transformation through struggle, and the balance of elemental forces. In comparing these creation myths, it's evident that every culture employs its unique symbols and narratives to explain the phenomena around them. Yet, common themes such as chaos transitioning into order, the significance of sacrifice, the interplay of elements, and the intimate connection between the divine, nature, and humanity are recurrent. These stories reveal much about the values, worldviews, and existential questions that have shaped human cultures across time and space. Faith plays a crucial role in understanding the creation of the universe, especially within the contexts of various religious and spiritual traditions, where it often serves as the bridge between the known and the unknown. While scientific methods rely on empirical evidence and reproducibility, faith encompasses a belief in principles and truths that transcend immediate sensory experience. This belief system offers a framework for interpreting the origins and purposes of the universe in ways that science alone may not address. In many religious traditions, faith is what allows believers to accept creation narratives and divine agency without requiring empirical evidence. For instance, in Christianity, faith in the Genesis account of creation is not necessarily about validating scientific claims, but about understanding the moral and spiritual lessons the narrative conveys. Faith in this context underscores a relationship with a divine creator, seen as loving, purposeful, and intimately involved with creation. Such faith helps to imbue existence with meaning, purpose, and a sense of order and destiny. Similarly, in Hinduism, faith in creation accounts as revealed in texts like the Rig Veda and the Upanishads involves accepting profound metaphysical truths about the nature of reality, the divine, and the self. For Hindus, faith can take the form of trust in cosmic principles such as Brahman and Dharma, helping to make sense of the intricate relationships between the physical and spiritual worlds, even if they transcend human understanding. Moreover, faith often complements scientific inquiry by offering narratives and principles that provide emotional and existential support. For example, while cosmologists study the Big Bang theory and the evolution of the universe, individuals of faith might see this scientific understanding as consistent with or reflective of divine creation, thereby integrating scientific knowledge with spiritual beliefs. This integration can lead to a more enriched worldview where the awe inspired by cosmic wonders deepens religious and spiritual significance. Faith also plays a role in ethical and moral dimensions of understanding the universe. By positing a creator or an ultimate principle, religious traditions provide a moral framework for human behavior. The belief in a purposeful creation often comes with an ethical mandate to care for the earth and humanity, seen as part of a divinely ordained order. Faith-based ethics concerning creation can motivate conservation efforts, social justice, and a sense of stewardship over the natural world. Yet faith is not without its challenges and tensions, particularly when confronting scientific explanations that seem to contradict traditional beliefs. These moments can lead to a dynamic interplay between reason and belief, pushing the faithful to reinterpret and reimagine their understandings in light of new evidence. This can result in a deeper, more nuanced faith, that accommodates both spiritual and scientific perspectives. Ultimately, the role of faith in understanding the creation of the universe is multifaceted. It serves to foster trust in a greater plan or purpose, provide existential meaning, inspire ethical living, and offer a harmonious integration with scientific insights. Faith does not contradict reason, but rather expands the scope of inquiry to include dimensions of human existence that science alone might not fully capture. The theory of a self-creating universe, often associated with the idea of a self-sufficient or self-referential cosmos, suggests that the universe could have originated and evolved without the necessity of an external creator. This concept draws from advancements in cosmology, quantum mechanics, and theoretical physics to propose mechanisms by which the universe could spontaneously arise from a state of nothingness or through the intrinsic properties of space-time and physics. One influential version of this theory is tied to quantum cosmology and the idea of quantum fluctuations. According to this perspective, rooted in the principles of quantum mechanics, the universe could have emerged from a quantum vacuum, a state that is not truly empty but rather teeming with potential energy and fleeting particles. Physicists like Stephen Hawking and James Hartle developed models suggesting that the universe could have originated as a quantum fluctuation, where a temporary perturbation in the quantum vacuum could give rise to a rapidly expanding universe. This process aligns with the Big Bang, but without requiring a pre-existing space-time or an external causal agent. The notion of a self-creating universe is also supported by the concept of the multiverse. In this framework, our universe may be one of many, each spontaneously generated according to different physical laws or constants. In some multiverse scenarios, bubble universes form within a larger inflating cosmos, each potentially springing into existence due to inherent properties of quantum fields. Such a multiverse doesn't necessitate a singular beginning, but instead includes a continual generation of universes, possibly making the question of an initial cause or creation less pertinent. Additionally, theories like the zero-energy universe hypothesis posit that the total energy of the universe might sum to zero. In this view, the positive energy of matter is perfectly balanced by the negative energy of gravity. This balance could imply that the universe as a whole might have emerged from a state requiring no net energy input, allowing for a self-sustaining creation process. Physicists like Alexander Vilenkin have proposed models where the universe tunnels into existence through quantum processes, suggesting a self-starting mechanism without the need for a pre-existing state or a divine creator. One important consideration in these theories is the application of the no-boundary proposal by Hawking and Hartle, which suggests that the universe might not have a definitive temporal beginning. Instead, time as we understand it could seamlessly blend with spatial dimensions in a way that avoids a singular starting point, akin to the surface of a sphere having no edge. This model hints at a self-contained universe, finite yet without a boundary in time, further supporting the plausibility of a self-creating cosmos. While these theories do not necessarily negate the possibility of a divine creator, they offer alternative frameworks in which the universe could potentially explain its own existence through natural laws and processes intrinsic to the fabric of reality. The idea of a self-creating universe invites us to consider the profound implications of quantum mechanics and cosmology, opening up new vistas for understanding our origins in potentially self-sufficient terms. The notion that natural laws can lead to the spontaneous creation of reality hinges on principles from quantum mechanics, relativity, and cosmology that describe how the universe might arise from a state of nothingness or a quantum vacuum. This idea posits that the universe can self-generate through physical processes without requiring an external agent or initial condition imposed from outside the framework of natural laws. One of the central concepts in this regard is quantum fluctuations. Quantum mechanics tells us that at a fundamental level, particles and energies are always in a state of flux due to the Heisenberg uncertainty principle. Even in what we perceive as a vacuum, there are transient changes in energy levels, leading to the spontaneous appearance and disappearance of particle pairs. In the framework of quantum cosmology, it's proposed that these fluctuations could cause regions of spacetime to momentarily form, potentially leading to the creation of a universe. The idea that vacuum fluctuations can give rise to entire universes is rooted in the fact that these fluctuations can produce sufficient conditions for a Big Bang-like event without requiring pre-existing conditions. The theory of cosmic inflation, introduced by Alan Guth and others, builds upon this quantum groundwork. Inflation suggests that right after the Big Bang, the universe underwent a rapid exponential expansion due to a high-energy state. Quantum fluctuations in this inflating universe could have caused regions of space to inflate at different rates, creating bubble universes. Our universe might just be one bubble among potentially countless others in a larger multiverse, each that popped into existence due to inherent properties of quantum fields. In addition to quantum mechanics, the principle of the zero-energy universe provides another pathway for spontaneous creation. According to this hypothesis, the net energy of the universe balances out to zero when considering the positive energy of matter and the negative energy of gravity. This balance implies that the universe could emerge from a vacuum state without violating conservation laws. The work of physicists like Stephen Hawking and Alexander Vilenkin elaborates on how quantum tunneling might allow a universe to essentially borrow energy from this vacuum state, thus bootstrapping itself into existence without any net energy cost. Hawking's no-boundary proposal, developed with James Hartle, provides a further dimension. This model suggests that the universe does not have a boundary in time. Instead, time might behave like a spatial dimension near the origin of the universe. This implies that the universe could emerge smoothly from a timeless state, avoiding the necessity of an initial singularity or an externally imposed beginning. In this view, the laws of physics themselves dictate the self-contained and self-sustaining origin of the universe. Additionally, the idea of spontaneous symmetry breaking in particle physics and cosmology suggests that the early universe started in a symmetric state, which then broke into the distinct forces and particles we observe today. This spontaneous process illustrates how simple, high-energy conditions can transition into the structured complexities of the current cosmos, guided entirely by natural laws. These theories collectively demonstrate that the universe's spontaneous creation can be explained through the lens of natural laws and fundamental physical processes. These processes do not necessitate an external creator, but rely on principles inherent to the nature of reality. By combining insights from quantum mechanics, general relativity, and cosmology, scientists construct models where the emergence of reality is a natural, albeit profoundly complex, outcome of the fabric of existence itself. This highlights the extraordinary capacity of natural laws to give rise to the vast and intricate universe we inhabit. Symmetry breaking plays a crucial role in the processes that may lead to the self-creation of the universe. This concept, rooted in physics and particularly in the domains of particle physics and cosmology, refers to situations where a system that initially exhibits symmetry ends up in a state that does not maintain that symmetry. This mechanism is fundamental because it helps explain how a simple, high-energy, symmetric state can evolve into a complex, diverse cosmos filled with structure and variety. In the early universe, shortly after the Big Bang, it is believed that conditions were extremely hot and dense, a state characterized by a high degree of symmetry. All the fundamental forces, gravitation, electromagnetism, and the strong and weak nuclear forces, might have been unified, appearing the same from all directions and points in time. As the universe expanded and cooled, this primordial symmetry was broken, causing these forces to distinguish themselves from one another through processes likened to phase transitions. For instance, consider the concept of spontaneous symmetry breaking, best exemplified by the Higgs mechanism in particle physics. The Higgs field permeates the universe, and its interaction with other elementary particles gives them mass. Initially, the Higgs field is symmetric, but as the universe cools, this symmetry is broken, resulting in the field acquiring a non-zero value. This change endows particles with mass and establishes the fundamental differences between particles, which in turn leads to the rich tapestry of matter and forces we observe today. Symmetry breaking also plays a pivotal role in the early stages of cosmic inflation. During inflation, a scalar field known as the inflaton field was uniform and exhibited symmetry. However, quantum fluctuations caused by the Heisenberg uncertainty principle disrupted this uniformity, seeding tiny random differences in energy density throughout the inflated universe. These minute perturbations were crucial because they would later evolve into the large-scale structures of galaxies, stars, and planets due to gravitational attraction. Additionally, grand unified theories and theories of everything, TOE, posit scenarios where symmetry breaking occurs at even higher energy scales, further elucidating how the intricate web of natural laws emerged from a more unified primordial framework. The sequence of symmetry-breaking phases signifies a transition from simplicity to complexity, marking the universe's path from a homogeneous state to one with varied particles, forces, and structures. On a more speculative level, some cosmological models suggest that the entire universe could have emerged from a symmetric vacuum state through processes involving quantum tunneling and fluctuations. The breaking of vacuum symmetry would be a critical step in transitioning from a nothingness or false vacuum to an inflationary state, ultimately giving rise to spacetime and its contents. Symmetry breaking is central to the concept of self-creation of the universe. It explains how from an initial symmetric, high-energy state, the universe evolves into a complex, structured cosmos. By breaking certain symmetries, fundamental forces and particles acquired their distinct identities and properties, leading to the rich and varied universe we observe today. This profound mechanism, deeply embedded in the natural laws, showcases the elegance and power of symmetry and its breaking in the cosmic narrative of self-creation. Feedback loops are fundamental processes that contribute to the self-creation and self-organization of complex systems, including the universe. By definition, a feedback loop is a system where outputs of a process are routed back as inputs, potentially modifying future outputs. These loops can be either positive, which amplify changes, or negative, which stabilize the system. In the context of cosmological and physical theories, feedback loops play a crucial role in driving the dynamic processes that lead to the emergence and evolution of the universe. One salient example of feedback loops in cosmology is the process of star formation. In the early universe, slight fluctuations in density, as described by the theory of inflation and quantum fluctuations, served as initial perturbations in the evenly distributed primordial gas. Under the influence of gravity, these denser regions attracted more matter, further increasing the density and gravity in those regions. This feedback loop continued until gas clouds became dense enough to trigger nuclear fusion, resulting in star formation. Stars, in turn, create heavier elements through nuclear synthesis, which are recycled into the interstellar medium when stars die. This recycling process enriches subsequent generations of stars and planetary systems with the necessary materials for complex chemistry and eventually life. In particle physics, feedback loops are integral to mechanisms that govern the behavior and properties of fundamental particles. For instance, the interaction between the Higgs field and elementary particles creates a feedback loop where particles acquire mass, influencing the behavior of the field itself. This mass acquisition is not a static process, but a dynamic equilibrium maintained by the interplay of forces described by the standard model of particle physics. Feedback loops also play a critical role in the large-scale structure of the universe. Gravitational interactions between galaxies, clusters of galaxies, and dark matter create complex feedback systems. The intricate web of cosmic structures emerges over billions of years through these interactions, illustrating how initial conditions can lead to incredibly diverse outcomes through iterative processes. In thermodynamics and statistical mechanics, feedback loops contribute to the emergence of order from apparent chaos. The concept of dissipative structures, introduced by Ilya Prigogine, demonstrates how systems far from equilibrium can self-organize into ordered patterns through feedback mechanisms. For example, chemical reactions in a highly non-equilibrium state can produce oscillatory behaviors and spatial patterns which are stabilized by feedback loops. Such principles can be extended to cosmological scenarios, suggesting that the universe's structure and complexity could arise from similar self-organizing principles. Another illustrative example is the concept of cosmic inflation. During the inflationary phase, the rapid expansion of the universe dwarfed quantum fluctuations to macroscopic scales. These fluctuations served as the seeds for all current large-scale structure. The inflationary field's dynamics involved feedback loops where energy density influenced the rate of expansion and vice versa, driving the rapid growth of spacetime itself. Moreover, feedback loops underpin theories related to the emergence of life and consciousness. The interplay between environmental conditions and biological processes creates a complex web of feedback loops that drive evolution and adaptation. Living organisms constantly interact with and modify their environments, which in turn influences their evolutionary trajectories. This bidirectional process illustrates how life can emerge and flourish due to these self-amplifying and self-regulating mechanisms. Feedback loops are central to the self-creation and evolution of reality. Through positive and negative feedback mechanisms, they enable the dynamic processes by which initial conditions lead to increasingly complex structures and behaviors. Whether in the formation of stars and galaxies, the behavior of fundamental particles, or the emergence of life, feedback loops underscore the interconnected and iterative nature of the cosmos. By understanding these processes, we gain insight into how the universe and the phenomena within it self-organizes, leading to the rich tapestry of reality we observe today. Imagine a universe that essentially creates itself, a concept that could stretch the boundaries of our understanding of existence itself. This idea is encapsulated in a theory known as the Bootstrap universe. In scientific terms, a Bootstrap universe is a self-sustaining loop where the universe brings itself into existence without an external cause. It's a mind-bending concept where the cosmos might be its own origin, linked by an intricate web of feedback loops that operate on the quantum level. One could think of it like a cosmic Ouroboros, the mythical serpent that consumes its own tail. In this model, every component of the universe is intricately connected and self-consistent, meaning the universe's laws and constants stabilize themselves in a delicate balance. Quantum fluctuations, small random changes in energy, could have spontaneously created particles and antiparticles that evolved and shaped the structure of the universe as we know it. This idea challenges our conventional notions of cause and effect, adding a mystical yet scientifically grounded layer to our understanding of the cosmos. Imagine the allure of contemplating a universe that is not just governed by the laws of physics, but one that inherently creates and preserves those very same laws in an infinite loop. The Bootstrap universe opens up a realm of possibilities, pushing us to rethink the origins and the very fabric of our reality. The principle of causality, the idea that every effect has a cause, is one of the bedrock concepts in science and our everyday understanding of how the world works. However, when we apply this principle to the notion of a self-creating universe, things get intriguingly complex. In a self-creating universe, such as the one proposed by the Bootstrap theory, causality takes on a peculiar and looped form. Here, the universe might be seen as both the cause and the effect of itself, challenging the straightforward linear progression of traditional causality. Imagine if the endpoint of a river was also its source, a scenario where the water seems to flow into itself, creating a continuous loop. On a cosmic scale, this means that time, space, and matter could be interconnected in ways that defy our usual temporally ordered cause and effect relationships. In quantum mechanics, where particles can exist in superpositions and entanglements, the Bootstrap universe doesn't violate causality, but rather operates within a more intricate version of it, one where the beginning and end are part of a singular, self-sustaining system. This paradigm suggests that our universe, with its physical laws and constants, might arise from a self-referential process, painting a picture of a cosmos that is not just a passive stage for events, but an active, self-initiating entity. It's a theory that pushes the boundaries of both physics and philosophy, inviting us to reconsider not just the origins of the universe, but the very nature of cause and effect itself. In the grand tapestry of the cosmos, information plays a surprisingly foundational role in the creation and maintenance of reality. At the quantum level, everything we consider to be matter is influenced and even constituted by information. Information in this sense is not just data or knowledge, but a fundamental component of the way particles behave and interact. Quantum particles, the building blocks of the universe, exist in a state of probabilities until they are observed, at which point they choose a specific state. This process of observation and measurement is, in effect, an exchange of information. Taking this further, physicist John Archibald Wheeler proposed the idea of it from bit, suggesting that every particle, every field of force, even the space-time continuum itself, derives its function, its very existence from binary choices, bits of information. In this view, the universe is a massive computation, continually crunching data to sustain its form and dynamics. Black holes offer a striking illustration of this concept. They famously devour matter and energy, but also seemingly disappear information. According to Stephen Hawking's theory of Hawking radiation, black holes can emit radiation that eventually causes them to evaporate, theoretically releasing the information they swallowed, albeit in an altered form. The framework of information theory also extends to how we understand entropy and the arrow of time. Entropy can be viewed as a measure of the information or disorder in a system. As entropy increases, the amount of usable information decreases, driving the universe towards thermodynamic equilibrium. This perspective opens a riveting window into the nature of reality itself, suggesting that the universe's evolution is an ever-complexifying network of informational transactions. Thus, reality may not just be a static framework we navigate, but a continuously unfolding narrative, written in the language of information, shaping and being shaped by the very fabric of existence. In a self-creating universe, emergent properties manifest as a result of intricate interactions at micro levels that give rise to complex new behaviors and characteristics at macro levels. Emergence is a phenomenon where simple rules or interactions among basic elements lead to unexpected higher-order patterns and functionalities. Think of it as the principle where the whole is greater than the sum of its parts. This concept is particularly fascinating when applied to the cosmos, as it suggests a dynamic interplay of fundamental forces that generate the complex structures and systems we observe. Take, for example, the self-creation described in theories like the Bootstrap universe or the holographic principle. At the smallest scales, quantum fluctuations act as seeds for emergent phenomena. These fluctuations can lead to the formation of particles, which interact through fundamental forces to form atoms, molecules, and eventually galaxies and biospheres. It's akin to a simple set of instructions leading to the blossoming of infinite possibilities. Within a self-creating universe, these emergent properties might include the laws of physics themselves. Initially, perhaps quantum rules and states fluctuate in such a way that they evolve into stable values and operations we recognize as gravity, electromagnetism, and nuclear forces. In terms of complexity, consider life itself an emergent property. A self-creating universe doesn't just form sterile structures. The same fundamental interactions that yield stars and galaxies can also lead to biochemical networks, giving rise to living organisms and, eventually, consciousness. This emergent complexity, arising from basic informational interactions, adds layers of depth and unpredictability to the universe, creating a rich tapestry of reality from simple, self-referential rules. The self-creating nature ensures that the universe is a continuous loop of genesis and evolution, with emergent properties acting as milestones in this ever-unfolding narrative. The philosophical implications of a self-creating universe are vast and profound, challenging long-held beliefs about existence, causality, and the nature of reality. A universe that creates itself calls into question the need for an initial cause or external creator, shifting the paradigm from a linear genesis narrative to a cyclical or self-referential one. This fundamentally alters our understanding of origins, suggesting that the universe is not a finite construct resulting from a singular event like the Big Bang, but an ongoing process where the cause and effect are intertwined in an eternal loop. One major philosophical implication is the reconsideration of the role of consciousness and observation in the universe. If the universe is self-creating, then the act of measurement and observation, which brings quantum states into reality, becomes not just a passive activity, but a participatory one. This suggests a universe where consciousness and matter are deeply linked, potentially implying that the cosmos is incomplete without observers to interact with and help shape its reality. This aligns with certain interpretations of quantum mechanics, such as the Copenhagen interpretation, which posits that particles exist in a state of probability until observed. Furthermore, a self-creating universe might support a more holistic view of existence, where all things are interconnected within a vast network of informational transactions and feedback loops. This interconnectedness could imply that every action, no matter how small, reverberates through the entire matrix of reality, reminiscent of the butterfly effect in chaos theory. Philosophically, it means that the universe is a dynamic, self-resolving entity where meaning and purpose arise from the complex interplay of its parts, rather than being imposed from outside. Lastly, this concept could lead to an existential re-evaluation. Humans, rather than perceiving themselves as products of a predetermined cosmic plan, might see themselves as active participants in a self-evolving universe, co-creators in a grand, ongoing process. This perspective invokes a sense of responsibility, underscoring the impact of human actions on the cosmic scale and inspiring a moral framework based on interconnectedness and stewardship. The self-creating universe posits a cosmos that is less a clockwork mechanism and more a living, breathing entity, relentlessly crafting its story in every moment. The concept of a self-creating universe fundamentally disrupts traditional views of creation, which often hinge on the notion of an initial cause or an external creator that sets everything into motion. Classically, religious and philosophical doctrines have posited a prime mover, whether a deity, a singularity, or a metaphysical principle, as the origin of everything that exists. This linear causality presents a clear beginning, typically framed as the moment of creation, followed by a sequential unfolding of the universe's history. In contrast, a self-creating universe implies that the cosmos is its own cause, operating under a cyclic or self-referential model that lacks a definable starting point. This self-sustaining loop challenges the deeply ingrained idea that every event must have a preceding cause and instead introduces a framework where the universe constantly regenerates and maintains itself through feedback loops and self-organizing principles. It also negates the necessity for an external agent or force that instigates creation, suggesting that the laws of physics and quantum mechanics innately possess the potential to bring the universe into existence and sustain it. This resonates with contemporary scientific ideas like the multiverse hypothesis and the holographic principle, which consider that our universe might be just one of many, each self-perpetuating and evolving according to its own intrinsic rules. From a metaphysical perspective, the self-creating universe compels us to rethink existential concepts like purpose and design. Traditional cosmologies often imbue the cosmos with intrinsic meaning and direction, provided by an external creator or through teleological principles, which imply an end goal or destiny. On the other hand, a self-creating universe suggests that meaning and purpose are emergent properties, arising from within the universe itself rather than being preordained. This perspective elevates the role of natural processes and interactions, implying that complexity, consciousness, and even ethical systems develop organically through the universe's self-referential evolution. The concept of a self-creating universe not only redefines the origins of existence, but also shifts our understanding of our place within the cosmos. It transforms the narrative from one of passive existence within a predetermined framework to an active participation in a ceaselessly creative and dynamic process. Do you believe the universe started from nothing? And are we really the only life in the universe? Let us know your thoughts and ideas in the comments below. Thanks for watching.